这个，我还是急着对这个，
往前翻，往后翻，
这个吧。
对，哎，不用往上翻。
我往上翻，我翻第一页，它怎么会不见呢？
是第一页，是这样的，第一页它有一页是黑的。
哦，
就你一直往前翻就能翻到第一页了。
好，
行。您是用中文讲、英文讲都可以。
英文呢？
英文 OK。
这里没中国人，还是有老外？有老外的话，
上午好像没看到有外国人。
万一他们
行，那就用英文讲啊。
好。
Okay. I think this is time. Let's get started. So welcome to the last day of the winter school. The first lecture of this morning session is Professor Jingwu Ye. Professor Ye is a great world-leading expert on condensed matter physics, and the famous SYK model was named after him and his collaborators. So today, Professor Ye is going to give us 2 lectures. He's going to talk about on the nature of temperature. So let's welcome him.
Okay, good morning. It's my pleasure to visit Yangtze River for the first time, and I thank Professor Jun to invite me to present this lecture to share with you this work on temperature. So, you know, I have been here for 5 days. I listened to a lot of good talks. So today I changed the tone a little bit because I'm a condensed matter theorist. So we know any experiment has to be performed at finite temperature, and the thermodynamic third law says zero temperature you can never be reached. So no matter how low it is, you always doing the experiment at finite temperature. So today I'm going to talk about this temperature from infinite space-time. Of course, in curved space-time, in general relativity, you have Hawking temperature. So that's a separate work, which I'm probably, if I get the chance, I'll talk the next time. So today I focused on the temperature in the flat space-time. So I'm from Great Bay University, which is a new university. Okay, this is our president, Professor Gang Tian. So I talk about what's the time. It's very difficult. Then today I talk about the simpler problem, temperature. But the temperature and the time we know from quantum field theory point is unified into a complex time. So that's the strategy I'm going to take. So if you talk about the temperature, you know temperature from undergraduate courses. So you have statistical mechanics. When you talk about the temperature, temperature determines the random motion. You have a law. You have a box of gas or particles. They interact with each other. Then it's the temperature which determines the random motion. The higher is more violent, the random motion. So I call it the internal energy. But even yesterday we chatted in the lunch, I never heard about the external energy. But in the conventional case, there's no need to distinguish internal energy from external energy. But however, if you have a system which is moving, then you have to introduce a new concept called external energy, which is different than internal energy in some cases. But we also know why temperature and time can be put into the same complex variable. You know, so what I mean is this. I would say all the previous talk is on zero temperature. Maybe yesterday Leon's talk about the temperature corrections. So we know the one over temperature is imaginary time. So Einstein's special relativity, space and the time. Okay, that's in the vacuum or for point particle. Space and the time are unified. go to finite temperature, you have to unify temperature and the real time into one complex variable. Okay, so that's the point. I'm going to use this point to discuss the nature of temperature and then its experiment consequences. Most of the students, you can always stop me at any time, okay, because I like discussions. I start with this slide means condensed matter physics and the particle physics share probably each half for the discovery of the concept. For example, symmetry breaking, or Higgs particle, like symmetry breaking, topological order, all origin idea come from condensed matter. Okay, so it was applied to particle physics, lead to Higgs boson, symmetry breaking due to P. Anderson. Of course, supersymmetry comes from particle physics because it's high energy, and Professor Lu talked about the M theory, Hong Lu talked about the general relativity, and Professor von Bohr talked about the scattering amplitude in quantum field theory or gravity, and all. So I think they covered them. Also, many other lectures covered this slide, and then also Professor Chen Bin covered the ADS-CFT. So this ADS-CFT correspondence. SYK completely comes from condensed matter. Okay, the original has nothing to do with string theory, but turns out it corresponds to lower dimensional gravity. So I would say, condensed matter, high energy physics, quantum information contribute equally to this slide. And this wonderful winter school covered most of this slide. So today, as a condensed matter physicist, I'm going to focus on symmetry breaking emergent phenomenon. So all these grades has been introduced by previous speakers. Special theory of relativity due to Poincaré, Einstein, Lorentz. That's well known. But what we learned from special theory of relativity is for point particle or in the vacuum at the zero, quantum field theory at the zero temperature has to have Lorentz invariance. That's well known. But today, I have to skip because previous people all talk about Einstein's general relativity, Hawking's radiation, and Einstein worked on statistical mechanics. Einstein worked on statistical mechanics from this Bose-Einstein condensation, superfluid helium Brownian motion. So also worked on quantum mechanics, there's EPR pair, and so Einstein worked on temperature also. So today I'm going to more focused on Anderson, which is a condensed matter giant. So what he said, more is different. So that means focused on non-relativistic systems. Okay, so I would like to stress in condensed matter system, if I have a chunk of materials which does not have Lorentz invariance. So when I start solid state physics, in high energy physics you get Dirac fermion, but in condensed matter you get Fermi C. Okay, in a solid, a metal, you get the Fermi C. Fermi C has no Lorentz invariance. So in materials, Lorentz invariance was explicitly broken. That's the point I really want to stress. So for analogy, in string theory, you have supersymmetry. It's easy to do calculation, but in QCD, you don't have supersymmetry. It was explicitly broken. But the Lorentz invariance supersymmetry are extremely important because it tells you the starting point. Then it got explicitly broken. So today, because Anderson stressed more is different, and means macroscopic number of particles will show collective or emergent quantum phenomenon. So a single particle does not show this kind of behavior. So I'm going to say emerging phenomenon probably include most of the discovery in condensed matter, like superconductor, superfluid. They're all quantum. Okay, it's not classical. You need quantum physics, quantum concept to explain superconductor, superfluid, ferromagnetism, quantum spin glass with disorder. This is SYK model. It was discovered from quantum spin glass. Has nothing to do with gravity. Only later, as Kita jumped in, to realize this chunk of material contains a lot of information on low-dimensional gravity. So, fractional quantum Hall effect, topological phases. There's also correspondence called the topological order symmetry correspondence, which differs from ADS-CFT, but shares some symmetry, shares some analogy. And so I would say more is different. This concept is extremely important. And I make an analogy here. Maybe Mao had the original idea and was more specifically pointed out by Anderson. Now this concept emerged in the space in ADS. ADS has an extra space. And in DS, then space-time is changing the role. Probably the time is also emergent. So I would say this emergent concept is expanded into emergent space and the emergent time. Probably the space-time are all emergent. So before I be more specific, I would say, in quantum matter, Lorentz invariance was explicitly broken at the very beginning, because even at the zero temperature, we have quantum matter. For example, we have a lattice system. Okay, it supports a lot of elements, supports a lot of emergent particles, emergent excitations. There's no Lorentz invariance anymore. I don't know. High energy people has a little bit hard time to accept we don't have in low energy condensed matter system. If we take a material, we do not have Lorentz invariance. So, however, Lorentz transformation, we can still go to different initial frame. We still prefer Lorentz transformation. So Lorentz transformation is different than Lorentz invariance, Lorentz covariance. We do not have Lorentz covariance, but we can still go to different initial frame. We still apply Lorentz transformation. I make an analogy, Yang and Lee's Nobel Prize is parity violation. Okay, their discovery is parity violation in weak interaction. But we know parity violation is different than parity conservation. Even there's no parity conservation, I can still apply parity transformation. It's just changing. So even we do not have Lorentz invariance, we go to different initial frame, we still apply Lorentz transformation. We may get a different answer.
You're only referring to the boost transformation, right? It's still isotropic.
Today I talk about the isotropic. You will still have rotational invariance, or like a superfluid helium, we even have translational invariance. But the solid, sometimes they even break translational invariance. They break a lot of high symmetry in particle physics. So that's what more is different. More is different means when you get a large number of particles, they show a lot of different phenomena than high energy physics. That's what Anderson's greatness was underestimated. For example, at the KITP, when I meet Joe Polinshinsky, the remuneration group, he discovered the remuneration group. The Nobel Prize was awarded to K.G. Wilson. So Polinshinsky told me, yeah. Anderson discovered the remuneration group, but he didn't get the credit for. But I would say people know, because when I was working on condo problems, they do this poor man scheduling. Oh, beautiful remuneration group. That's at least 15 years before K.G. Wilson. But the people know, okay. So
how to define this absolute frame?
Yeah, that's a nice question. Let me give you a specific example. We do have absolute frame in condensed matter system or at the let me give one example. Maybe I should give this example to answer this smart question. For example, I take a superfluid system. So in ITP a week ago, I made the experiment with Seamus Davis. We charted very nicely, very fruitfully. So he's a leading expert on superfluid. For superfluid, okay, is a three-body system. In vacuum with special relativity, we have, for example, a ruler is moving. This or the observer, only two-body problem. In condensed matter, we have three-body problem. For example, superfluid is flowing. There is a container which holds the superfluid, and also there's an observer. Okay, so we have three-body problem. One is the reservoir, which determines absolute frame, which is not moving. Usually the reservoir, the container, you have to hold something. And then the sample is moving. This is a macroscopic sample, contains a lot of particles. And then there's the observer, the experiment is. So it's a three-body problem. So that's why we do have absolute frame. But that doesn't mean Einstein is perfectly right, okay? In a vacuum, two-point particle is only relative motion. You have to satisfy, Lorentz covariance. That's for sure. But if you go to Anderson's, more is different. You have to say it's a three-body problem, and there is a container which says that because you perform experiment. So my approach is starting from condensed matter system, which has a reservoir, and the superfluid can flow without resistance. So it's easy for them to, you put the injection, they start to flow without resistance. Then we make the experiment, we make all kinds of detection. So that's why I would say but we still apply Lorentz transformation. Even Lorentz invariance was broken. Even we have absolute frame, we still apply Lorentz transformation. The answer may change. And that's the something we have to adjust to is because there's no Lorentz covariance anymore. Maybe different reference frame see different answers, and then is any experiment results or not. So so let me jump to what I like to say. Okay, special relativity condensed matter system or quantum statistical mechanics. Actually, statistical mechanics we know is about condensed matter system at the finite temperature. Okay, so special relativity was, in vacuum at the zero temperature. How to push it to finite temperature? It's kind of very interesting, but very tricky. Of course, many people worked on this problem before. Okay, since the special theory of relativity, Einstein immediately, because Einstein worked on statistical mechanics, he worked on BEC. He discovered there is a BEC. Okay, Bose-Einstein condensation is Einstein condensation. Okay, and Planck, he discovered quantum mechanics by black body radiation. Black body radiation is at the finite temperature, and the photon they emit radiation. There is that's black body radiation. It is also statistical mechanics. So they know they want to apply special theory relativity to statistical mechanics. So their way is that at that time, I don't think there is a quantum field theory at that time. No quantum field theory, okay? But there is sort of quantum mechanics. So there is the thermodynamics. They start from thermodynamics phenomenologically. So Einstein wrote several papers. So he asked the problem is, oh, okay, we say this special serial relativity is, they excluded the ether. Okay, in the vacuum, we know there's a special serial relativity. There are a lot of sharp predictions. 2-point particle, if a ruler is moving, it gets shorter. If a clock gets slower, that's all experiment tested. Now, obviously, they want to apply to statistical mechanics. These people just don't teach this in the undergraduate. Because in the undergraduate, you learn the quantum mechanics, and the special serial relativity is very easy to push the quantum mechanics to spatial theory combine to get the Dirac equation. That's very easy. Single particle. Single particle, you cannot define temperature. Nobody defines temperature for single particle. For temperature, you have to have a large number of particles. They interact with each other, and then to describe their internal motion a statistical way, because you don't know each particle doing what. We don't care about it anymore, too many. Then we look at their collective behavior, use one quantity, temperature, to describe. That's called the statistical mechanics. But a single particle still apply, for example, quantum mechanics. You can combine with special relativity easily to go to Dirac equation, and then quantum field theory. All require Lorentz events. However, when you combine with large number of particles, in condensed matter is 10 to the power 23. In cold atom, it's less, it's 10 to the power 6. But it's still a macroscopic number of particles. Then you cannot capture single particle anymore because it's too complicated. We have to look at the collective behavior. At that time, thermodynamics is already more or less mature. So they start from this thermodynamics behavior first, second law, trying to look at how temperature transforms. So Einstein said there's a body with temperature T. Then we start to move. What happened to its temperature? So they address this problem, these big names, Planck, Einstein, Pauli, Laue. Then the first find if a body is moving, the temperature increase. Okay. And somehow they made one exception. Then they make another assumption. Einstein found the different answer, get less. I think the first found the increase, then a decrease. Okay. Then Einstein fear both had some problems, and he quit it. So the original article was in German, and then he said, then many people follow, say, oh, the temperature does not change, or temperature is not defined. It's not very good. There's no more temperature. And now, by accident, I look at this problem, but from a very different approach. Because at that time, I do not think the approach from thermodynamics trying to fit this, that, make this assumption, this is not the right approach. The right approach is very fundamental. Just time and then temperature has to be, to find out the temperature, the time has to be complex. Of course, Professor von Bohr gave a very nice lecture. He talked about the scattering amplitude. He has to complexify all the momentum. But here, I'm more specific. I complex the time. The time has two components. Then, if time and the temperature actually is one over temperature, I put on the same footing. Then the transformation law of the temperature may come automatically. But why we complexify? This comes from quantum field theory. Go to finite temperature. We know the imaginary time, the periodicity in the imaginary time becomes the temperature. So first of all, I have to define what's temperature. What is temperature? Many people say, well, temperature is temperature. Of course, temperature. So when we have to see what's the temperature. Then I would say, because there is a reservoir, if we go to canonical ensemble in statistical mechanics, statistical mechanics has 3 ensembles: canonical ensemble, microcanonical, and grand canonical ensemble. Okay, so in most of the case, in condensed matter system, is always canonical ensemble. That means there's a huge reservoir. Like this Yanqi level is huge. The temperature is fixed. Okay, they determine the temperature. When any sample interact with some small interaction, collide with the reservoir, they will achieve the temperature of the reservoir. And then there's an observer. Then these 2 cases are different now, because the sample is moving relative to the reservoir. Okay, there's a relative motion between reservoir and the sample. Another is the sample and the reservoir no fixed, no motion. The observer runs backwards. These 2 cases are very different. If there's no reservoir, sample becomes a point particle. Einstein said there's only relative motion. They're the same. The ruler is moving, or the observer, there's no absolute motion. Ruler is moving or observer is moving, who cares? As long as there's a relative velocity. This Einstein said that they're equivalent. We just perform Lorentz transformation, you get all this nice answer. But here it's different. We have a big guy who sets the rule. Does this contradict with Einstein? No, because Einstein did not say. Of course, Einstein tried to apply to phenomenology, but he didn't start from statistical point of view. When we learned statistical mechanics in undergraduate, but somehow you never people don't want to combine with special theory of relativity, because that's controversial. And also, people don't learn this. But here I'm saying it can be combined in this way. So these 2 cases are very different. Okay, it's not equivalent. Most condensed matter system, there is a huge guy which sets up the temperature. Okay, and there is an absolute frame. I don't know you get upset or not. There is an absolute frame in condensed matter system. Anybody get upset? But actually, this has been, Professor. Yeah. Anderson already said, actually Anderson already pointed out when he didn't say it explicitly, means condensed matter system has no Lorentz invariance. Okay, quantum Hall superconductor. Okay, so A and B we have to distinguish. Actually, in particle, black hole in ADS is this case. I chatted with Jun and other people. Black hole in ADS, okay, they don't have reservoir. The temperature is well defined. In DS, that's very different. Okay, in DS it becomes an open system. And particle experiment, I will say, is also the temperature is so high you don't have a reservoir. It's an isolated system. Okay. Okay. So I take this superfluid as an example to explain condensed matter system. Means we have a reservoir, a sample, and an observer. It's a 3-body problem. So actually, I will show you why this answer is correct. So when the superfluid is not moving, thermodynamic zero law, or no, it's zero law. That's zero law says the temperature has to be the same. Okay. So they collide with each other. At the end of the day, they reach equilibrium. These experiments, they cannot control the temperature of the superfluid because it's inside the container. They can only heat it up or lower the temperature of the container. However, when superfluid starts moving, observer is not moving. Then by using temperature and the time are unified, then you conclude the temperature slightly higher is a relativistic effect. Velocity v is higher than the reservoir. So this does many students upset. They say, oh, because at reach equilibrium, the temperature should be the same. Yeah, if there's no relative motion, the temperature has to be the same. However, when there's a relative motion, the temperature has to be slightly higher for them to reach equilibrium. That's the answer, which is a little bit counterintuitive, but I will explain the physical picture very soon. So that's the major answer, at least in the first lecture. Maybe second lecture, I want to demonstrate this answer from all kinds of views. But Einstein said this, from a very, anyway, at the end of the day, he don't know which answer. But we will show this answer is the correct answer. Okay.
So you suggest that to combine temperature with the time.
Yeah.
Is it possible
Real
to
time.
derive this from time dilation?
Yeah, it's similar, but not. Has to be very careful. I will derive it using similar sense, but it's different. Okay. Yeah, it's related. Okay, so I will talk about the case A first. Case B, when you have to be ready. Case B, if there's a temperature T, when the observer is running, the temperature will not change. So that's because the internal energy is different from external energy. So case B, I will list the answer here. I want to make one slide here. B is, suppose I go to microcolonic ensemble. The reservoir and the sample combined, observer is not moving, or is moving opposite. So microcolonic ensemble, these are the same. But these may not be the same. Okay, even if the isolated system moving is different than the observer moving. I will explain this a little bit more. So particle experiment is more or less like this. So I couldn't demonstrate. For example, a black hole observer is moving is different than a black hole is moving. So I want I believe this is a little bit tricky without the reservoir. Let me focus on the reservoir case. Okay, so let me start what's temperature. I take a Carter's book. I don't know which textbook are you using in learning statistical mechanics. Wang Zicheng? Which book? Anyone tell me? You all learn the statistical mechanics. Which textbook do you like most? Can you tell me? Which book? Carter's book. I think Carter's book is good. So Carter's book, but there's a tricky thing. Maybe I'm not. Actually, Carter is a big guy. His reservoir has temperature T. This is a canonic ensemble. I bring any sample which is much smaller than the reservoir. When they reach equilibrium, there should be a temperature T. So, and then we can, the reservoir is much, much larger than the system. Okay. So we can define, I will split, take any state of the system, I sum over the reservoir, then I will get the canonic ensemble. So the canonic ensemble, the temperature is the reservoir, the big guy's entropy over the energy. Okay, that comes from thermodynamic first law. So in canonic ensemble, the temperature is given by the reservoir. It's all reservoir because the reservoir is big. The sample has to reach its temperature. So that's the temperature definition of the reservoir. Of course, that's the canonic ensemble. Okay, gives the temperature. Then we calculate the partition function. Okay, so that's so But there is thing, I even don't think Kada really wrote it clear. When the reservoir and the sample reach the equilibrium, that you have to have some thermal interaction. That means they collide with each other. Otherwise, they will not reach temperature. At the end of the day, you can think of when they reach equilibrium, you can send the Epson goes to zero. When they're ready, then more or less the sample becomes an isolated system. But you need to bring it in contact with the reservoir first, and then you can 中文叫过河拆桥，达到平衡以后 I roll this big guy away。我先用一个大人物先爬上去了，爬上去后把大人物给扔掉，就 more or less okay. Let's reach the temperature. So I would say reservoir is the most natural thing to define the temperature. For microcooling ensemble is a little bit tricky. So there's always debate, but one of the terms is also giving energy, because the microcooling is giving energy. So the energy is given. The microcooling, the energy is given. Then there's the entropy. Then with energy change a little bit, entropy changes. That also defines the temperature of the microcooling ensemble. But the microcooling ensemble, we know, I want to see this ETH. Microcooling ensemble has a problem, because for non-interacting systems, you never reach equilibrium on your own. For example, we talk about free ideal gas. Ideal gas never reach equilibrium on its own, because why? They never interact with each other. You take, for example, you take a free electron gas, they will never reach equilibrium without a reservoir. If you take an isolated system, all the electrons not interacting, they can never reach equilibrium because they don't interact. But we still introduce temperature. Why? Because we can put a reservoir. Anyway, I don't understand this. When I was an undergraduate, I never thought about it this way. Oh, free gas, ideal gas, just get temperature. But if they don't interact with each other, how they get the temperature? You have to bring a big guy with temperature T close to it, so they collide. Each particle can collide with the reservoir, but they don't interact with each other. Then they get the temperature T. So that's the way to get the temperature.
So why can't it have like self-interaction?
For free gas or free electron, they don't have interaction with another particle.
Yeah, but usually for ideal gas, you introduce a very effective self-interaction that assume they reach equilibrium by the.
Oh, that's not free gas anymore. That's an interacting system. So strictly say free system, we introduce temperature by external reservoir. They don't interact with each other. We still do Fermi Bose distribution function. The temperature comes from external reservoir. If they don't interact, there's no way, because we don't care about each other. How we reach the same temperature? But there's an external reservoir set up the standard. Oh, I'm the big guy, or you're a small guy, talk to me, get the same temperature. But all these particles, they still don't interact with each other, because the reservoir is so big. For example, the Earth is so big. I kick the Earth once, or that student kicks the Earth. They are independent, because the Earth is too heavy. There's no way to exchange the Earth such that we talk to each other. No way, because the reservoir is so big. Okay, so ideal Bose gas, how the temperature, or even this photon gas. When we talk about black body radiation, the photon, a box of photons, they don't interact with each other. Where the temperature come from? You think the photon can interact with each other? They don't interact with each other. Professor Fenbo showed from scattering amplitude, they say abelian gauge field don't interact. If they don't interact, you don't get the temperature by your own. You need help. You need a big guy to help us. All this, then to get the temperature. So black body radiation is a typical example. Photons don't interact with each other, but they get temperature by external reservoir. You have a box to hold it. You heat up the box. Then you don't have Lorentz invariance. Black body ratio has no Lorentz invariance. Okay, so even all the integrable model, they don't reach temperature on its own. Like a rational conformal field theory, they have an infinite number of generators. Professor Yang, I think he will talk about the integrable system. The integrable system, you don't get temperature on its own. If you use microchronic ensemble, no way. You never get the temperature. You have to introduce a reservoir to reach the temperature. We can still talk about the statistical mechanics. So that means integrable system, if initially stay in a given orbit, it stays there forever because it's integrable. However, for example, this photon gas, okay, today I'm not going to talk about black hole. Black body radiation, okay, is really need a reservoir, okay. It's black body radiation. Here I would like to skip a little bit this because I explained ADS is like a condensed matter system. DS is like an open system. Okay. So I probably skip this. Okay, so particle experiment, particle physics, how they get the temperature? They collide, they get a cloud. This cloud of particles are very high energy scattering, get very high temperature. Of course, you don't have reservoir because the reservoir, how can you get this high temperature? They cannot measure this temperature. Their clouds, they measure the transport energy. That looks like fit the temperature is very high. So in this case, okay, I would say there's no reservoir. It's a microchronic ensemble. These particles are strongly interacting, but the number of particles is very small. It's strictly speaking, it's not an equilibrium system. But approximately, we can say it's a microchronic ensemble, given temperature. Okay, but they keep saying, for example, they keep saying is with the temperature T chemical potential. They keep saying it's grand canonic ensemble. That's not right. Okay, mathematically you can introduce. Actually, I think should be fixed energy, fixed number of particles, but you can mathematically perform Lagrange transformation of temperature T and the chemical potential. But that's they keep saying is microchronic ensemble is not right. Okay. Even in black hole, people introduce chemical potential or temperature. It's a microchronic ensemble. It's a mathematical trick. Okay. But the real system is microchronic ensemble. In ADS space, we are talking about the microchronic ensemble. Okay, so my conclusion is in case A, there's a relative motion between the sample and the reservoir. The temperature is reservoir, when sample is moving, the reservoir does not care because the reservoir is so big. Because I'm a big guy, or do whatever you want, I will not be affected. Otherwise, why call him big guy? The Yanchi level, you take some water out or put some water in, he doesn't care because it's still Yanchi Lake. He's a big guy. The big guy's temperature never changes because it's a big guy. When sample is moving, its temperature a little bit higher to get the equilibrium. This comes from, as Jun said, similar to time transformation. I will show that. But this case, when the observer is moving opposite, the temperature will not change. Why? Because the observer do whatever you want. It does not affect the internal motion. Internal means now I can tell you what's internally. Is the heat reservoir and the sample, they're internal. They determine the internal energy. Observer determines the external energy. The observer, so in this case, internal energy is different than external energy. Observer still see Doppler shift. What he sees is external energy. Does not affect the internal energy. Therefore, the temperature does not change. So, I will. How much time for the first lecture? I want.
It's up to you. You can find some point to
Yeah. So I will stop maybe in about 8 minutes. Okay. I want to stop at the point. So that's I'm going to demonstrate is using helium-4. Okay, to demonstrate case A. So let me say special theory of relativity finite temperature split into two sectors. Okay, the first sector is observer plus sample. Okay, so this is controlled by the real time. There's another sector is reservoir, because the three-body problem, the reservoir plus sample. This determines the temperature. The reservoir and the sample, their bodies. Oh, we determine the temperature. Forget about this observer. Independent of observer. Okay. So the temperature is determined by their relative motion. Okay. So I find the temperature independent of the observer. Okay. Then the observer, the sample is he is a smart guy. He wants to make a relation with reservoir. He also wants, say, make observer say, oh, we are the body. We don't forget about the reservoir. We determine Doppler shift energy. We determine external energy. Okay. So there's a Doppler shift energy. Okay. There's an internal energy, and then in some cases they are not the same. So for case A, the temperature, because there's a relative motion that determines the temperature. These two guys determine the temperature. And then in this case, of course, in case A, oh, sorry. I need, in case A, because the observer is not moving, the heat reservoir is also not moving, only sample is moving. So in this case, external energy equal to internal energy, because the observer is not moving. For case B, because there's no relative motion between reservoir and the sample, the temperature is fixed, they're the same. Observer is not moving, does not affect the temperature, but they affect the external energy. So in case B 是里外不一 observer, so the observer see the temperature when the observer see the same temperature, but because the temperature has been fixed, but they see Doppler shifts are different. So in this case, internal energy is not the same as the external energy. So that's why I introduced external energy. I want to say a few words before I go to the next section. Now I give the answer. Now I want to demonstrate the answer. For case A,
and then the internal and external I could be negative.
Yeah, you. So that's a nice question. And for example, that's not the focus. Here, if the because it's superfluid system when, but in high energy physics, if you perform Lorentz transformation, because then you never see any transition. Why? Because of the speed of light. The boost can never be above the speed of light. So this will never become negative in high energy physics. Different than initial frame, you just see Lorentz shift because the speed of light is big. But in condensed matter system, this could become negative because now the omega, I will talk about that. Their speed is not the speed of light, it's some intrinsic velocity. It could become negative. It becomes negative if it's in internal energy, they induce quantum phase transition. Because superfluid, there is a critical velocity. When you're above that, it goes to another phase. But in high energy physics, people don't care about this because speed of light is the god. You boost or whatever you want, you cannot approach the speed of light. You never see the energy becomes negative. But in condensed matter system, you see it go to different phase. So that's what Anderson said. More is different. It's always different. Because in condensed matter, see a lot of phenomena you cannot see in high energy physics. But that's a different topic. In case A, internal energy equal to the external energy, but the temperature changes a little bit. In case B, the temperature is the same, but the internal energy is not equal to the external energy. Okay. So case A and B is quite representative. I come from this answer from, I write partition function in terms of partial integral. And then this, I will say in canonical sample, in a static sample, if the sample is not moving, that's in the standard textbook, statistical mechanics, which connect quantum field theory with statistical mechanics, just by one stroke. You go to imaginary time, the temperature. Okay. That's what Einstein didn't know at that time, 1950. Okay. Einstein passed away in 1953. But before, this is 1970 or 80, people realized how to make a connection between quantum field theory and condensed matter is go to Euclidean space and then define the periodicity as a temperature. So here, what I'm going to do is, actually, this is not enough. The imaginary has to be complex, both imaginary and the real part, and the imaginary part. One part is real time, another part is temperature. So maybe I finish this derivation, then we can quit. Oh, it's my, okay, let me finish this derivation, then how I get that? Jun already get a hint. So I would say static sample, okay, reservoir, it's a three-body problem now. How you apply Lorentz transformation is tricky. It's a three-body problem. It's a two-body problem. It's not a two-body problem. Two-body problem, you just say, observer change, you shift the reference frame. I prefer Lorentz transformation. I go there, whatever you like. But here is a three-body problem. Then I have to go to imaginary time. We know this is just, I have to define a strange frame. It's not strange, it's just a co-moving star frame. We know co-moving frame. I finished this, we quit, but we relax 5 minutes. There's a co-moving frame when the ruler is moving, there's an observer moving together with the ruler. That's called a co-moving frame. Okay, then we transform from a co-moving frame to another frame, you get the result. Here I introduce a co-moving star frame. Co-moving star frame is reservoir and observer. They are moving together with the sample. Means all the three guys are moving. In this case, the same as they are not moving. But the experiment, you can never go to co-moving star frame. But I can imagine, because reservoir is not, in experiment, the reservoir is big. Nobody can touch it. Okay, it's defined. The co-moving frame, we know the temperature is T. Okay, then I perform a transformation to the from co-moving frame to the lab frame, to case A. Because the three body, but the reservoir and the observer are attached together. Only sample is moving. Then co-moving frame, co-moving star frame, go to the lab frame. I do this transformation. I skip this. Then, so in this co-moving star frame, okay, yeah, we know the temperature is better. Because co-moving star, all the three guys moving together is like static. We know the temperature is T. Then go to the lab frame. So I have to cancel this. In the lab frame, we have to have the same x prime. We cancel each other, we get the temperature is higher. Because in the lab frame, I have to, the same position, I define the periodicity in the lab frame. Because I know co-moving frame, the temperature is T. Co-moving frame, we know the temperature. I want to derive what's in the lab frame. In the lab frame, x prime has to be cancelled because the time was complexified. But what about the space? So I'm different than Professor von Bohr. He complexified all the four momentum. I only complex the time. Because the space, if you complexify, people will ask you, if you complex the space, what's the imaginary part of the space? What is the physical meaning? I don't know. There's no physical meaning. Because at any finite temperature, space-time is not unified. At the little temperature, space-time unified, but we know space-time, I don't know, bin years or bin. Space-time is never the same because time has a causality. It's just when you go to Euclidean space, the things mix each other. But if we go to finite temperature, temperature is the periodicity in the imaginary time. And they're not the same. Of course, you break Lorentz image. Fine, I don't have a Lorentz image at the very beginning. So I don't complex the space. If I complex the space, I will run into very big trouble. Because the imaginary part of the space, what it is, you can say, oh, it's hidden, it's not measurable. No, people will not accept it. Space stays as 3 dimensions. Only time goes to complex. In this case, I make this, actually I have to say, this also has a little bit of assumption, means space is not complexified. So I have to exclude the extra time. So in light frame, I have to look at the temperature, the same space, look at the periodicity. So this periodicity, definitely the expand does not appear. So I got this get bigger. A moving body gets hotter. So I need 2 minutes, then we go to break. If I take C goes to infinity, that's non-relativistic limit. And then the temperature stays the same. So it's a completely relativistic effect. That's why it's so hard to see. However, if the velocity goes to C, then it becomes extremely hot. Even the reservoir is temperature T. The guy is moving so fast, close to the speed of light, it will boil down, it will melt itself, because even the theory may break down. So, but in non-relativity limit, you don't see this. And okay, let me, of course, the zero temperature goes to zero temperature because it's a ratio. If T is 0, it goes to 0. So it will not change the third law. Okay, maybe I start with superfluid, then there is a critical velocity. So that's why the velocity cannot be too high. As Zhong Yuan asked, there is a critical velocity. If your boost velocity is too high, it's not superfluid anymore. So that's why this formula is very difficult to test. Now I stop here. Here I would say I derived the case A. There are several other cases. Okay, for case A, internal energy is the same as external energy. But in other case, they may start to split. So I stop here. We have 5 minutes break. I will, rest of the lecture, I will give you physical interpretation of this. You got this answer, you may not be very comfortable. But let me give you some physical explanation. Okay, see you in 5 minutes.
你如果把时间孵化了，你在做论文自变化，你的空间自动就是缩。
对，空间自然就有个 I， 但是呢，这个空间呢，我还是实的 ，Ix 就是虚的。
对，那这个意味着什么？
这个意味着就是说，空间的这个虚部只要不局限在任何物理量，我没有把空间把它变成复数，我空间乘以 I， 我空间还是实数，我这个时间不一样了，我时间把它复数化以后，它就真是一个复数了，它有实部有虚部，你空间做罗伦兹变换。 算这个 scattering amplitude 投成 generative function。我是11点，我是10点50就得结束是吧？
对，最好是10点50
行，
稍微超几分钟，
超1-2分钟可以。
你把这个话筒带上。Okay, let's continue the lecture. So Professor Ye will continue the discussion on temperature.
So I want to give a little bit because I want to make this more intuitive, how to understand this answer, okay? So I would say the temperature and the 类人呐、internal energy， 你这个，比如说一个人他这个他嘴里说的跟他肚子里的想的还是有时候是不一样的，就是这个意思，是吧？这个你想的你都说出来是不太可能，你说出来的有时候跟类人有时候一致，大部分情况都一致，也有不一致的时候。我想就是这个意思。我想 ，so internal energy determined by the relative motion between sample and the reservoir, independent of the observer. The energy, the temperature was determined. The observer, no matter what you do, they get the same temperature. That's something I want to stress. Okay. However, the thermodynamics also involve the volume. Then is thermal quantity, is extensive quantity. There's also Doppler shift energy. Then we have to say what's the observer. When I derive this temperature, I use this co-moving star frame. That means the observer and the reservoir are the same. They're not moving. But the observer can say, why should I be static? I can also start to move. The observer can move. Okay, in this case, well, the role of the observer, I can say, so that's two typical cases. Okay. I would say in case A, we just say observer and the reservoir are not moving. Okay. Reservoir never move. Observer static to the reservoir. In this case, the temperature I made the transformation. The volume is the same because volume has nothing to do with temperature. It's like a special theory relativity. You get a little bit smaller. Okay, in this case, internal energy equal to the Doppler shift energy. 内外一致 because observer and the reservoir are not moving. And then case B means this V1, V2 is V1 is the velocity of the sample, V2 is the velocity of the observer. In case A is only sample is moving, but the observer is not moving. I have two velocity now, sample and observer. But in special theory relativity, only the relative velocity. You only have one velocity, the relative velocity between observer and then the sample or point particle. But here I depend on V1, V2 separately. Why? Because there is an absolute frame. That's the difference in special theory relativity at the zero temperature. Velocity, we have absolute motion. So we need to specify both V1 and V2, not just the difference. So for case A, is V1 equal to V2 equal to 0. So in this case, internal energy equal to Doppler shift energy. And for case B, sample is not moving. Only the observer is moving. In this case, the temperature is not changing. But the volume, observer is moving, they still see the volume. The volume of the sample still change. Because it's Einstein's special theory relativity. Okay. In this case, the internal energy is the same as the static case. Why? Because the sample and the sample and the reservoir are not moving, so they determine internal energy. However, the observer is moving, they still see Doppler shift. This is external energy. 外人. If you go to statistical mechanics book, you never see people 外人. But 如果有个内人，当然有个外人啊。但是大家为什么不提呢？ Because in the standard textbook, they're the same. And even for case A, they're also the same. But for case B, they're not the same. 里外不一. 内冷和外冷不一样。It could happen. It happened in this case. Of course, both are moving. In this case, then you will see the temperature has gamma 1. Volume is the relative velocity. Because this is the structure, this is semiconductor. Okay. In this case, gamma 1 not equal to gamma 1 2. Internal energy not equal to Doppler shift energy. So 里外不一了，这个情况里外不一。我想打个比方，比如说你跑步，你不跑的时候就很平静，你跑起来以后，可能你说话就有点费力了，就这个意思。Okay, co-moving case. Let me say, people they ask this question. Okay, in a superfluid case, for example, superfluid case, I want to stress this part. This part people had a dispute with me. For superfluid, okay, for superfluid, it's moving. I measure this temperature. The static observer measures this temperature. People always ask, okay, suppose I do an experiment. The observer is moving together with the reservoir. It's called co-moving. What temperature did it get? It still gets this temperature. Why? Because the internal energy is determined by the reservoir and the superfluid. Has nothing to do with observer. Observer not moving or moving together with the sample, you get the same temperature because it's independent of the observer. Physically is 内冷不依赖于你这个 observer, independent of observer. Observer keep running, so what? You just change your own speed. Does not affect 我们的内冷。内冷是跟 reservoir 决定了的。That's why the temperature will not change. So in this case, co-moving case, the temperature is still the same. It's gamma 1 determined by velocity of the relative to the reservoir. But the volume, co-moving frame, they're moving together with the superfluid. They don't see Doppler energy anymore because they're moving together. The volume, the system volume is the same. Okay, in this case, so that's why the co-moving frame is different than the co-moving star frame. Okay, so co-moving frame, you see the same temperature as before. So this Doppler shifted, but they don't see Doppler shifted energy anymore but the internal energy is still there because the reservoir and the sample is still relative motion. So this I want to stress is when the sample and the reservoir there's relative motion, the temperature is fixed. Maybe one ball is on another girl static, they get the same temperature. Because 内冷，我们的内部的事情你别来管我，就是这个，不要干涉我的内政，就是这个 reservoir 跟 sample 是内政的。你 observer 你爱怎么动怎么动，我们的温度就是这样，你爱看不看就这个 temperature， 你怎么动都是这个 temperature。That's why I want to stress. This in the superfluid system, I know is completely right because I did the microscopic calculation when C goes to infinity. Okay, I also challenge the experiment. This explains a lot of this distinguish between 内冷和外冷explain a lot of exotic phenomena. Okay, so in general case, I would say the temperature, actually this is very intuitive because volume and the temperature. Temperature can be considered as a finite size in the imaginary time direction. Okay, the volume is the finite size in space dimension. Temperature is the finite size in the imaginary time dimension. So they transform slightly different. One is internal energy, another is combined with Doppler shift energy. Okay, So I want to explain this process a little bit physically. Why the temperature changes from a physical picture. For example, when a sample and the reservoir reach equilibrium, the temperature is T. Okay. Now it starts to move. I have to do something, right, to make it move. Because the sample and the heat reservoir exchange heat. So you have to do some work. How it speed up to a finite velocity? I push it, then you do work. The work goes to the sample, and some heat goes to the reservoir. Okay, so energy conservation, the two heat plus some kinetic energy. Of course, second law is always entropy increase. So this process, when it reach the equilibrium, there's no more heat. So there's no more heat. I want to say is for canonical ensemble, then when they reach the equilibrium, there's no more heat go to the sample because it's reached equilibrium. But there's still some, because there's still some exchange between the heat reservoir. Therefore, the reach equilibrium, there's still heat go to the heat reservoir, but the reservoir temperature will not change. Why? Because you provide some heat to the reservoir temperature will not change because reservoir is a big guy. You give some heat, specific heat is infinite. The temperature will never change in this case because 你到雁西湖去，你倒一杯水和拉一杯水进来，它的这个水面不会变，它太大了。你这一点算什么呢 ？Here is the same. The reservoir temperature will not change, but the sample has finite specific. The temperature will increase. However, the temperature increase you have to be very careful because the temperature increase is an intrinsic part. There is also heat part. Okay, so when reach equilibrium, there's only heat. There's no more heat go to the system. They go to the heat reservoir. But there's two parts because there's a collision, the temperature change, but there's also due to the collision, the friction part. Then my claim is, if 我就过河车桥，我把这个 Epsilon goes to zero, reduce this part. Then my bet is the intrinsic part will have a slightly higher temperature than the heat reservoir. That's my claim. At the end of the day, 我达到平衡以后 I remove the contact with the reservoir, get rid of the friction part, you will get the intrinsic part. Let me explain this. You hopefully clear in your confusion. From maybe you keep your question, okay? Now from this Lorentz algebra, we know. I want to explain the physics is Lorentz algebra. Then C goes to infinity, goes to Galileo algebra. Okay, so I want to explain the physics is. We know Lorentz algebra, they have conservation of energy momentum and then also angular momentum, also center of mass momentum. So why the temperature change a little bit? First, let me understand C equal to infinity. When C equal to infinity, Lorentz algebra go to Newtonian algebra. Okay, in this case, temperature will not change. T prime equal to T. Because we know that's why in Newtonian mechanics, any motion, it could be decomposed into a center of mass motion plus an internal motion around the center of mass. You can do that perfectly in Newtonian mechanics. Is that right? You learned this. So in this case, you can push the sample, you transfer it to its kinetic energy. Will not touch its internal motion because they are decoupled anyway. That's why c goes to infinity, t prime. I want to explain why is the relativistic effect. However, why at any finite c? In this case, you can actually it's not center of mass anymore. It's called the center of momentum. Classically, center of momentum, then there's no way to decouple. There's no such center of mass theory anymore. If you learn mechanics, only in Newtonian mechanics, center of mass decouple with the, I can get a center of mass and then I do whatever to center of mass, because center of mass, even in center of mass, is not an initial frame. It's always decomposed into two motion. But for relativistic effect, no, because relativity you get this square root. There's no way to decouple center of momentum from its internal motion. So in this case, I want to say is because I push this sample, relativistically, this will also affect the internal motion. Therefore, the temperature will be slightly higher. And then the higher would be independent of velocity, could be with scale. So mostly likely answer, the temperature is higher. From physically is how to understand this. Because when the reservoir has temperature T, another guy is moving. Why that guy's temperature is slightly higher? Why? Because we know if there is a temperature difference, there is a heat transfer between higher temperature to lower temperature. That's true when the two sides are not moving, there's no relative motion. But now if there is a relative motion, why that moving guy has a slightly higher temperature? Then they reach equilibrium. And I would say this is because, you know, in the reservoir, all these thermal particles, they are static. So they're just random motion. But for this moving sample, all these molecules, they do two jobs. One, they have to move. There's a uniform motion. At the same time, there's a random motion. They couple to each other. Of course, the temperature should be slightly higher because I do two things. Because one boy is talking to me. I'm running. My temperature should be higher than you because I'm running. And then my temperature higher so I can keep the same, because I have to keep my motion. So talk with you at the same frequency. I feel a little bit hotter than you because I do two jobs. You only do one job. Anyway, this is physical interpretation. Because for me, my approach is always trying to give physical interpretation. Yeah.
Is there a heat transfer from hotter to?
Exactly. That's what I said. If we are not relative motion, we have the same temperature. If I higher than you, there's a heat transfer. If there's no relative motion. But if you stay there, I start to running, then my temperature should be slightly higher to reach equilibrium because I do two jobs. You only talk to me. You are not moving. 你以逸待劳. But I have to moving. Moving, then my temperature should do two jobs. One is keep me moving. Another is talk to you. So, but these two motions are not decoupled. Only in C into infinity, they're completely decoupled. But at the finite C, I have to have slightly higher temperature to keep talking to you with the same frequency.
If there's some heat transfer.
There's no heat transfer because I'm moving. There's no, to reach equilibrium, I have to be slightly higher than you, such that there is no heat transfer. That's my claim.
That means that two different.
You are still using the concept with static sample. Static sample, you are right. But I'm moving.
Yeah, your conclusion is something counterintuitive.
Yeah, but it's not really that counterintuitive. Because I'm moving, and the molecule in your body is random motion with no constant motion. The molecule in my body, there is a constant motion. At the same time, there's a random motion. They couple to each other. So in order for my random motion match your random motion, get the same temperature, I have to move a little bit fast because the molecule in my body, they do two jobs. They have to keep moving. At the same time, I have to talk to you.
So anyway, the upshot is you predict, in this case, two objects with different temperature. There is no heat transfer between these.
No heat transfer, but there is a relative motion, constant motion. That constant motion make my temperature slightly higher than you. It's a completely relativistic effect. So
quite similar with the situation when you calculating the temperature of radiation, the temperature in the horizon and the temperature in the infinity.
Oh, that's called that's slightly different. That's Tolman effect. I will make this comparison. It's a little bit there is some similarity, but different. In the relative side, it's called the Tolman effect due to the gravity. Yeah, I will make a comparison at the end of the slide. They are related, but different. This is Tolman effect. That's what they mentioned. The Tolman effect. Yeah. Okay. Now at the end of the day, I will say, what's the experiment? You make this prediction. The experiment, what did we say? So unfortunately, oh, there's one thing. How much time I have? Okay. 20 minutes. It's okay. So how to test this? At the end of the day, there's one analogy I forgot to. Actually, I like to say this because it's related to particle physics. I also have a little bit of time. Suppose I push this sample, then the temperature definitely increase. I predict when I remove 过河车桥, when I reach Riverland, I remove the big guy. 很多人都是这样嘛，我先找个 big guy 爬上去以后，过河就拆桥了。那么你剩下来的这个温度，我把它叫intrinsic velocity.
There's no heat transfer from the sample to the reservoir. Instead, the equivalent would be that you keep push the sample, you work on it, and it keep transfer it to the reservoir.
Oh, look, here is in order to keep the sample moving, I only need to apply infinite force to count the friction. So this is actually is called a non-equilibrium steady state. In this case, there's no heat to the sample anymore. Only this heat will goes to the reservoir. And then, but if I put the Epson goes to 0, even these are not needed. So what I mean from here, I conclude, I think this is right. Although, so if I push, if I move this connection with the reservoir, it looks like an isolated system. Then I conclude, get back to Einstein's original problem. If I push a microcoulombic ensemble, okay, microcoulombic, no reservoir, then because of relativistic effect, I push a box of gas, a particle, the kinetic energy increase. But because the motion, there's no decoupling between send-off momentum and the internal motion. So the temperature still increase. For non-relativistic case, you push a box, the temperature, because they decouple, you just change the velocity without touching the internal motion. But here I conclude, even for microcoulombic ensemble, the temperature still increase, even for microcoulombic ensemble. So if I use these, but how to test this experimentally? Unfortunately, this effect is very small. For if I use condensed matter system with chloronic ensemble, the velocity is very small. In the superfluid helium, the velocity is only 60 kilometer per second. If you after that, it's not superfluid anymore. Because why I want the superfluid? Because superfluid, even this part does not exist. Because superfluid is flow without resistance. There's no friction. So there's always no this part, only this intrinsic part. So use superfluid. This experiment is very easy to perform, but this effect is very small. And then, yeah, I want to say one more thing. Talk about the temperature and the volume, as I said. What about the other physical quantities? Many people will say, okay, there are many papers, but why I don't like these papers? There are probably thousands of papers on combined spatial security with into thermodynamics. Very complicated papers. But why I like my opposite? First of all, my point is clear, statistical mechanics. Then temperature and the time are combined into complex. That's it. Very, very clean. I don't play with this thermodynamic relation. Then the two general transformation is universal. One is volume, one another is temperature. I drew this. I used that picture. The volume, how volume transform. The temperature, how it transform. Because both are finite size. One is finite size in space. Another is finite size in imaginary time. So they transform, get the same fact, but in case say the same fact. So this is very intuitive. Okay. Also looks very correct. I don't play with thermodynamic relations. Extremely complicated. The many papers extremely complicated. You don't know. I don't think they remember what they did. Here I remember because it's a very clean calculation, statistical mechanics, and also plus complex time, but not a complex space. Okay. So at the end of the day, if you look at the free energy, for this experiment, I thought in particle physics how to test this velocity, this temperature effect. Particle physics, because the big equipment cannot move. Then there's the cloud. If you make the cloud move, but how you do that? If you make the cloud move with high velocity, then it may the temperature will increase further. That's my prediction. But how you make that colliding cloud move, I find this very difficult. They do this experiment? They usually do this center of momentum zero region, the cloud expand. If you make it move, the temperature will also increase. But I don't think that experiment can be done. So we have to resort to condensed matter. But the condensed matter, the problem is the velocity is very low. So if I plug in, we get this. Before I talk about the results, I have a few minutes. I want to see this free energy stuff. I talk about the volume. I talk about the temperature. You ask what happened to the free energy. So then, free energy, volume, and the temperature is very universal, independent of all the microscopic detail. As I said, it's just finite size in space, finite size in the imaginary time. They transform very similarly. But for free energy, for a relativistic system, for a specific case, I know how to do the transformation. You see, we know the free energy. For superfluid, there's a collective excitation. What is the emergent particle? Oh, there's an emergent Gauss-Stone boson, there's an emergent rotor mode. I also call the massive scalar. So that is the excitation. All these are the sample, the collective excitation is not the element particle anymore. Okay, it's not like a particle physics is with the speed of light, all these element particles. These are emergent particles. It's collective excitation. If I know the collective excitation, I can get the free energy of the system. That's easy because the systems are interacting. The systems are interacting. The emergent particle are not, I got the emergent particle on top of it, okay? So I got free energy. KBT, volume, and density of states. I can also get the number of particles. Of course, it's not conserved. It's like a photon. The number of particles is not conserved. Then the density of states. For the case A, how I transfer the free energy? As I said, for case A, then you just do Doppler, you perform, because you go to a different reference frame, you just perform the Lorentz transformation. Lorentz symmetry was broken, but I still prefer Lorentz transformation. There's no problem with that. As I said, the Lorentz transformation and the Lorentz symmetry are different things. I still have 10 minutes, I can finish. So this energy and the momentum I perform Lorentz transformation. The temperature volume is universal, independent of micro detail. But this energy excitation depends on what kind of sample. Okay. Then I perform Lorentz transformation on both momentum and the frequency. So I can do this transformation. Then I can see this fact is Bose distribution. You can see this gamma get cancelled. So here, this factor actually you don't see relativity effect. The temperature and the Doppler transformation get cancelled. So it's very similar to non-relativity because it gets cancelled. It's the same thing when you're not going to see this effect. You get cancelled. However, the density of states, you can still see these major changes. So you can see when the momentum transform, there's a Jacobian, because you have to perform the law. We do this momentum and the frequency transformation at the same time. Okay. So you can see this Jacobian also appears. So here indeed depends on the velocity. So this you have, even if it gets cancelled in that Bose-Einstein distribution. So it still depends on this velocity. That's what I mean. So this spectrum can be mapped by neutron scattering. And unfortunately, this fact is very small. You look at V over C squared is 10 to the power 15. So is this measurable or not? This is kind of temperature effect. Okay. So actually, you compare with gravitational wave, is 10 to the minus 20. This is gravitational wave is 10 to the minus 21. The frequency due to gravitational wave shift. So that has been measured. So here is 6 order of magnitude bigger. So I don't know how to measure, but definitely atomic clock Junyi's group is close to gravitational wave. Gravitational wave, the tiny effect has been measured. So this temperature effect can be measured, definitely. What I like to say is, even if it gets cancelled in this Bose-Einstein distribution, it appears in the density of states. So I like to say is the temperature and the volume transformation is very universal. But the free energy has to depend on what kind of excitation you are having. Okay. Depends on the specific. That's why I addressed all these problems. I avoided. I started from statistical mechanics. Started from the time has to be complex, include both real time and the temperature. Both are important. Okay. Because when the system is moving, real time is important. Temperature is also important. So maybe I have 10 more minutes. Okay. So I want to say, summarize, because this is special theory relativity. Okay. Length, time, and mass, and also Doppler shift. Then the temperature is a new unit. Okay. Temperature is Kelvin, is a new unit, and in this case, it's for equilibrium system, the status is the same as the temperature for equilibrium system. Therefore, the temperature for case B is not the same. So for case A, there's an increase. That student they mentioned the Tolman effect. In the gravity side, there's a horizon radius. It's very similar formula, but the physics are different. So this is called the Tolman effect. I don't have time to explain. It's all T over tau, coordinate time over there. But this derivation is really tricky. Okay, as I said, it involves a lot of physics. But then the end of the day is similar to this Tolman effect. So why, as I said, let me get back to Planck, Einstein. I think their angle has a lot of limitation due to the time, because they start from thermodynamics, not statistical mechanics. So that's the difference. Also, statistical mechanics automatically unify temperature and the time. And so in case A, I got temperature increase, internal energy equal to Doppler shift energy. But for case B, they didn't distinguish these cases. Okay. So this thermodynamics is very complicated, easy to make mistake. So I take a different route. I think I resolved this problem is when case A, the temperature increase. Case B, they didn't distinguish these cases. Okay, because they did not start from the statistical point of view. Of course, there could be a black hole side story. That is more, or maybe we can chat some next time. Before I conclude, I want to explain one small thing. I have a few more minutes here because a student asked me, I skipped that slide about, I'm talking about the equilibrium system. A student said, what about the non-equilibrium system? Non-equilibrium system, actually, I want to make one slide to explain maybe it's also related to statistical mechanics. What do we mean by statistical mechanics? How we distinguish equilibrium system with yeah. So maybe so I'm talking about the equilibrium system, which has a well-defined temperature. But one student asked me, what about for open system? They interact with a reservoir environment. You see, for equilibrium system, there is an interaction, but the difference goes to zero. At the end of the day, after reach equilibrium, there's the epsilon effect. Even Carter didn't discuss it carefully. So when epsilon goes to 过河拆桥以后 then actually the equilibrium system with a finite temperature T. But the open system is a strong interaction. Epsilon goes to 1, it's non-equilibrium system. So this is look at looks like quantum optics. Okay, so for equilibrium system, the density matrix satisfies Heisenberg equation of motion, and you can, when you reach equilibrium, you can derive canonical ensemble. For non-equilibrium system, For non-equilibrium system, you get this density matrix is a master equation, okay? Because there is a bus, there is a dissipation described by gamma, and if you drop the jump, then you get this so-called non-Hermitian. So in this case, equilibrium system has well-defined temperature. That's what I'm discussing. For non-equilibrium system, the temperature is not defined. Then you don't need this temperature concept, just real time. Okay, that's the main difference. And then I would say this corresponds to the ADS geometry. This corresponds to DS geometry, because DS geometry is this is open universe. That's definitely a non-equilibrium system. And I focused on this equilibrium system, which has temperature, both temperature and real time. In non-equilibrium system, you can just forget about the temperature. Okay, thank you very much.
Thanks, Professor Ye, for the very interesting talk. Any more questions?
Yeah, Zhongyuan has a question. I don't know my answer it or not. I saw the student had a lot of questions in there. Can you continue to ask? Yeah.
So you say you mean if there is an observer is moving, so he will observe this original system will be a different temperature, right?
No, what I mean is when observer is moving, as long as the reservoir and the sample is their relative motion fixed. Yeah. No matter observer what moving, how he moves, will not affect the temperature, because the temperature is determined by the internal motion between the reservoir and the sample. So the observer can move together with the sample or not moving or whatever. The temperature will not change. What will change is the volume and the Doppler shift energy. For example, I measure the Doppler shift energy, that's external energy. It will not appear in the free energy. In the free energy part, all these are internal energy. That's why in this free energy part, I want to say if you calculate the system's free energy, this is the important question. Okay, for example, if I calculate the system's internal energy, if the sample is not moving, you just perform all this calculation, specific heat, whatever. However, when sample is moving, so for example, the superfluid is moving, what's this energy? This energy is the internal energy. We're not suppose case B, the observer is moving. It will look at what will the measure. They will measure Doppler shift energy. But that Doppler shift energy, you cannot plug it here. Plug it here is internal energy, because the reservoir and the sample is not moving, so they will not move. But the only change is the volume. So what plugged in free energy, all these guys are internal energy. That's what I want to stress. If you look at the case B, the sample and the observer are not moving. The sample and reservoir, but the observer is moving. Observer will measure Doppler shift, of course, because he's moving. But that Doppler shift energy you cannot plug in here.
Okay.
What plugged in here is determined by the reservoir, is internal energy. So that means 里外不一。我这个跑动的人看到的是外人，但是外人你不能放在free energy 里面，free energy 是内人。
Okay, thank you.
我的 physical interpretation is when you are running, you change the kinetic energy of your own. Right? Why should I? But the internal energy of the sample will not care about you.
Yeah.
Because you do whatever you want, you run 1 meter per second or whatever. you measure the Doppler shift. And also Zhongyuan asked the Doppler shift could change the sign. Okay? Now I want to stress this. This is important because I chatted with this experimentalist. I got a lot of, response from him. If you measure Doppler shift energy, actually system has this slope. If you run fast enough, for example, this velocity is 60 meters per second. Suppose you riding a very fast stuff past 60 meters per second. What will you see? You will see Doppler shift energy becomes negative. But the system does not care because the internal energy is not moving. It's not. This is case A. Okay, I'm talking about the case B. This is explained. If you run fast enough, the Doppler shift energy will change sign. That's what you see by you, but the system will not have phase transition because that's you. What you see is a superficial case. However, if the sample is moving, when sufficiently fast, indeed it goes to a different phase. So that's explained a lot of phenomenon which you cannot explain by special theory relativity. From special theory relativity, naively, whoever moves should see the same thing. But here it's very different. Sample moving, you see phase transition. Observer moving, you see nothing. But you see something. You see Doppler shift. But what you saw is 外人，就相当于我心里想怎么想，我怎么说，反正我怎么说都行，反正不影响我的内心，就是这个意思。This is a good analogy. Yeah, good question. Yeah.
Okay. Could I also have another question?
Yeah.
So could you turn the slides to the discussion about the particle physics? That diagram.
Particle physics. Yeah. I would like to say a few words about particle. I forgot. The particle physics. That diagram is, first of all, I want to criticize these people keep saying grand canonical ensemble. This is not grand canonical ensemble. But why they want to use chemical potential? They just a mathematical trick. There's no reservoir. Okay, there's no reservoir to exchange particle with the system.
Okay.
But I mean, if I could do an experiment, make the cloud moving, then it will also have this effect. But how? I don't know how. Experiment particle physics is very hard to manipulate things. How you make this colliding clouds moving? What's your question?
Okay, my question is, so you see, when we describe the star system, we should use a micro canonical ensemble. But I think this is not true because in the cosmology, we know the universe is expanding.
Yeah.
So the energy is not conserved.
Right.
So we can only define the temperature, but so what I mean is that in cosmology we should use temperature but not the energy. So maybe we could use somehow canonical ensemble but not the micro canonical.
You are right. You are perfectly right. That's I answered this. I think I said this. You expanding universe, you have to be very careful. It's a non-equilibrium system. Okay, it's not no energy, no temperature. Okay, that's what I mean. In expanding universe, you don't know what it is. Energy is not conserved, temperature is not well defined. But I would say this. Expanding universe is more like this open system. Okay. I just explained this slide. Give me one more second. Okay. Yeah. It's more like DS geometry, or in this case, energy is not conserved. With Jun, we charted this DS geometry. There's a called cosmological horizon. outside the cosmological horizon what it is. We don't know, and the expanding universe, the metric is time dependent. That's really not the case here because energy is not conserved. The temperature, people use microwave background, 3.7K. That's an approximation. If the expansion at the given short period of time is quite the equilibrium. If the expanding is, if I look at the time scale, much smaller than the universal time, approximately we treated it with some temperature. Yeah. But if you look at the global picture, it's really not the thing I'm talking about because we don't know. It's an open system. There could be something big outside. Both temperature and energy is not well defined. Very nice question.
Okay, due to the time limit, for more questions, please ask Professor Ye in private.
Thank you.
So let's thank him for 2 very inspiring talks.
多谢。哎，我把这个给抽了啊，直接抽了啊。好。
您在这儿，您的所有的温度的定义应该都是
统先拿下来
应该都是相对能量的偏或者微分的那个。那个从那个定义导出来的那个。
那个你讲的是这个我还没有文件，这个真正的推导，
不需要考试吧，就直接换，
我觉得
都可以。
这
种没问题。
我现在是倒过来，就假定这个，我就对撞的，
就是考到这个电脑考不考都。
爬进去帮你就是
考生可能
是不是我没有这个推导比较，我一直没有推导。我现在这个推导就是应该把这个推进去看头啊，真正的推导我没有推，就是看推进去看头，把这个时间到复数法，
考到这个地方，考到这，
实不是温度，是周期，虚不就是实时，然后我要做个变换，但是没有，但是我想这个结果是对的。Very nice。
您不是说这个温度它和速度相关，但是安鲁效应不是说温度它和加速度相关。
哦，你这个问题我问的你应该在那个时候问。安鲁是这样看，安鲁效应是这个 observer 加速运动我这是匀速，你这个加速 observer 加速运动，看到那个它有一个温度的。有一个温度，这是我的吧？
这都是您的。
我的喝完。对，我应该提一下安鲁效应，没有时间。安鲁效应不一样，它是有个加速运动然后呢，零温变有限。我这是有限温变有限温，但是就微小。我这是，而且那个安鲁效应是不一样的。安鲁效应它是一个零温的东西变成有限温。跟加速度成正比。
但是你觉得很奇怪，就是温度它到底是和观测者的什么运动关系？因为你这个如果是和速度有关系，就是惯性行到另一个关系。对。但是如果是加速，就是从一个到那个非惯性，所以它温度它这个温度是加速。
安鲁效应安鲁效应它是安鲁效应它是跟那个安鲁的。安鲁效应有加速度，我这个安鲁效应第一是不矛盾。比如说因为我是这个我是 t 等于0还是 t 偏它那个是我这是 t prime over t 很好。如果对应温度是0 t prime 也是这个跟安鲁效应就是说，跟你的考虑就是考虑周特性这个温度。对，让人都不知道是所以包括这个安鲁效应。但是我们确实讨论问题是，如果让你说这个对，那我们说安鲁效应是这个就是有它每是每个最大不一样，也就是说，
它应该一直在变。
所以说这个时候我们看，所以这个加速度是常数的话，它是怎么的？这个按钮相应我今天不在提，它是如果这是一个中空是零，一个 Q state， 然后我加速运动以后呢，我就看到一个叫 Hindler Horizon，Hindler Horizon 呢，我这里 Hindler 在从外面我看不到，我就把它 trace 掉，就是一个 Q state 到 mix state，mix state 就有个温度，这个温度就证明它的加速度。这个物理跟我这个完全不一样，因为我这个 case B 还有点像 case B 我连续运动我温度不变，case B 的温度是不变的。阿姆效应是在 case B 的情况下找到加速度。我的 case B 就是一个连续运动温度是不变的，就是 regular， 阿姆效应。
你们这那个上课的要求吗？上课。
阿姆效应还是常用的，是这个分通，它有的是加速的执行。看到上面的来，然后那个我其实我不讲你一方面的，那个就是这个跟阿姆效应这个是独立的，对 case B 你看我连续运动我温度不变，
现在是的这些课堂
case B 啊，我认为它
设计，折算出来的，
这个物理不一样，阿姆效应现在可以，我这里都是外面的，
可能就是
但是我主要想知道温度到底是温度应该算是什么？因为它是比较大，其实不缺老师，
温度啊，
也这个那个研究出来老师都可以来分析。就是我们，当然我们比如说我们自己配备以后，参与的话，我们肯定要教学，但是我们得自己去争取，不会有人给我们
温度显
看那个课，所以我们必须要自己去争取一个课然后来上。
这么多，就是想一想这个时间，
跟你们天
没有，
就是时间变成 flex 了，还有这个空间配备，但是空间没有变。
对，
但是我其实
很难割舍，很难调整。这个你就刚好就是有这个，因为看得上去只能写上去，
但是你把时间放边幅化之后，
反正用中文讲就不用讲东西。
我把某个量，很多老师把所有的一个都给我看成了 SO13，反正就是它
因为因为讲的话，
这个时候的群
当然应该没有太大的
这个群呢，
一个是会
一
个本来就
我其实当时想问他，我不是写，
不是这是，
但是他这块他也是我们优多变化，他也是它和那个阿姆效应就跟我们这个研究量也不一样，这个
跟阿姆效应完全不一样，阿姆效应
对啊，我
阿姆效应
有点这个是，它就是
阿姆是阿姆效应
也是美国的一个院系，但我们也是意大利的 ICTP 的分部。
Q state 变成 mix state。
所以前几天实际上是有几个，为什么在这个时候办？就是因为我们有国际顾问，就前几天有几个外国老师，他当场讲课就回去了。
首先我是连续运动的话温度不变，我现在就缺一个。
然后下午就是您的报告之后还有一个，就是他会给一堂课，就是那种组成的 public lecture。他现在是 IPMU 的主任，就日本东京大学，东京大学有个
这两个都很好。然后做变换，做变换的时候，就看到温度的改变。
物理学会有点
温度给这个温度上140度，
一个是
从某种情况下 A 对应的是一样。
可能是，我觉得就是说，反正就是说，比如说高能理论，就是日本最有名的就是一个东大的 IPMU， 还有京都大学的
可以作为
因为这两个所长都是
但是稀土线没有一个没有一个它是证据不在有刚刚是配合我是但是这些结果我去的时候是退休的，因为那个多出的没有结果，民主运动之后，加速运动就其实最重要的是不知道那个我特别想做的一个是做高的，但是没有人做后知后，就是说安鲁效应是明文建成规有国企是30分的对教授。安鲁效应我发现我不是把我一加速我变成一点，我一开始不是你们我再做安鲁效应，一开始
反正基本上都是日本。
我再做，物理界的大佬。我猜了一下，是因为它加速不，对，先有个量的系统，系统有个问题。然后安鲁效应是系统为零，它就是一个真空，然后加速就看那个你这个玩意我看那个
这个是
就是得
挂在这上，挂一下的。行，我就挂上来。我还是拉上来。
因为这个我们线上转播，它就是不会扩音，但是你必须这样讲，线上才能听见。
哦，行，好。是我带有茶，我是。
就是上下翻页，最上面那个就激光笔，它得再翻一页，就有时候黑的时候你再翻一页就行。
好。
哎，这个但是不知道为什么大家不配合，这才是一个真正的，就是你把你问的问题可能也跟懂。
Okay, let's continue. So, the third lecture of this morning session, we're very happy to have Professor Wenli Yang from Northwestern University. So Professor Yang is a great expert on integrable models, and he's gonna give us 2 lectures. So, the first one this morning, the second one this afternoon. So the title of his lecture is Quantum Integrable Systems and Their Solutions. Let's welcome Professor Yang.
首先我开始我用中文来讲，lecture 的话我用英文来讲，就是首先我非常荣幸来参加这个，实际上是非常有历史的，因为现在你们这一代人的话，你们可能就是觉得什么东西也许这些都是很自然的 ，ICTP 这个机构实际上是。对于我自己上学的是80年代86年进的大学，90年上的研究生。那么在90年代那个年代的时候，实际上互联网并没有在中国普及。我是95年去的 ICTP， 那么当时给我看到的是一个完全崭新的不一样的一个视野吧。在某种程度上，咱们国内当时还是非常的跟国外的差距还是非常大的，而且呢，年轻人的这种机会也是非常少的。那么当时开阔了我的眼界，那完全一个崭新的一个。后来回来当然我们中国现在发展的非常的快，到现在为止，那么现在互联网所有的我们几乎所有国际上所有的信息都可以很快就能得到。那么很大程度上，作为我个人的这个成长的过程中，受到了 ICTP 这样给我的这样的一个机会。当时是他们资助，我96年博士毕业，95年去的那个地方。那么这个在学术上提高了眼界，同时呢各种技术上提高了眼界。那么比我再长一些的，现在在国外的不管是在国外的，我不知道叶老师知道不？早期咱们国内 ICTP 是第一个跳板，咱们国内很多人出国的话，一个是受到了李先生的一个 Caspia 的一个支持，咱们国内的特别是物理方面的人出国是通过这样的一个渠道，那个渠道应该是在 在我想一想，应该是在78年、79年到89之后结束了。另外一个就是很大的一个地方呢，大家都是通过 ICTP， 那么物理的、数学的，实际上也有。我在国外也碰到很多老师，很资深的老师，他们是通过，所以我个人也是受益。那么现在呢，在吴老师的争取下，咱们中国 ICTP 也有这样的一个机构。我想全世界是不是中国和巴西？
可能
非洲还有。那么这样的一个机构，当然现在对你们来说，出国各种情况都不存在任何的问题。那么实际上这个也看到了咱们中国的发展，也看到了，吴老师实际上是给咱们国内的年轻人提供了一个非常好的一个平台。好，那么这是我个人的感觉。那么年老师说这个事情了以后，我觉得我非常希望来参加这样的一个活动。好，那么再次感谢祝会给我这样的一个机会，我也能在这儿来呢跟大家分享一下我前面这些年的一些工作。好了，那 I try to speak in English, so I will give two lectures. Actually, this is most based on the work during the past 20 years, more than 20 years. So the quantum integral system and the solution. Actually, Professor Ye gave the very important example as SYK model. SYK model is the particular exact solvable models below to the CFT, and the CFT is a big branch of the quantum integral system. So I try to give the quantum integral system overall about the most important one is the conserved charge. So integral system means they have a lot of conserved charge. CFT, they have a lot of conserved charge. And for all the model here, I am mostly based on the spin chain. They have a lot of the conserved charge. And also we know from the physics, especially for the理论力学. Actually, we know that if the system have the symmetry, then they correspond to have the one conserved charge. If they have enough symmetry, that means if the conserved charge, that means commute conserved charge. That is for the classical mechanics, that they should in the Poisson bracket commute each other. And in the quantum system, actually commute each other the conserved charge. If the number of conserved charge is equal to the freedom of the system, that's the half of the dimension of the phase space, then the system integral. And that means in the picture, in the action and the angular momentum, use the kinetic transformation. That means the classical system. Then you have the picture that all the freedom factorized. That means the system becomes the, if the degree of the, the space of the phase space is 2n. That means you have the n independent particles. They almost have no interaction. This is the main picture. This is from the classical view to think about that. In a quantum system, and that means, I think Professor C.N. Yang gave a very important contribution to the quantum integral system. That means the scatter of the system, the quantum particle, that means can factorize. If the system is the spectral can factorize, that means the system is integral system, which guarantee this happened. That is conserved charge. If you have enough conserved charge, if you think about the classical system, that means factorize to the independent system. So the quantum case, that means, so very important, very important to guarantee the system is integral. That is the Yang-Bass equation. Yang, in Professor Yang's picture, that this system factorized. That means the n-particle scatter matrix can decompose into of the two particles interaction scatter matrix. That means the all the factorize. Let's have the constraint on the two body. Very important is two body scatter matrix. So the three body scatter matrix can decompose in two ways by the product of the two particle scatter matrix. And this actually gave the equal, because finite physics results is equal each other, is only one. So that should equal each other. That is the Yang-Bass equation. So I will, actually all my talk based on the integral system based on the Yang-Bass equation. So Yang-Bass, that means the Yang-Bass equation is very important to describe the quantum integral system. So actually, let's start. Quantum integral system, as I gave the overall picture, that is enough conserved charge, guaranteeing you can, for classical finite dimension systems, that you can use the action and the angular momentum. That system is factorized. You can solve it. And in a quantum system, I just gave some picture about new. Of course, the first example is the classical dynamic system, Newton dynamic series plus gravity. We can solve actually for the one particle in the center. So for the solar systems, our Earth around the sun. That means you can solve everything. We know that the angular moment, because this this potential only depends on the distance of our Earth between the Earth and the sun, and also is 1/r. 1/r potential. That means this doesn't actually have the rotation, three-dimensional rotation. So that's the angular momentum is conserved charge. And the angular momentum, that means fixed position and first momentum. Then you know that this system is the angular momentum, the angular momentum, the particle actually on the one plane because there's a particular interaction. And also they have this angular momentum as the conserved charge. And actually because the 1/r potential, they have another rotation, another conserved charge. This may be not very familiar with you. Actually, longer, the first one who gave this particular conserved charge. This is enough to solve this one. That means we know that the orbit is circle or elliptic circle or some kind of the if you use this one, I'm not where can we speak， 或者是行星走的那个轨道。那么 only have this exact solution can prove the Kepler-3 theorem. And another example is the Schrödinger equation, quantum mechanics Schrödinger equation for the hydrogen atom, we know all the solution. And then this actually gave the fundamental of the spectrum of all the systems, spectrum for all the atoms. Another one, maybe if you start the mechanics, static mechanics, very important one is to the IC model, because this has a very belong to the quantum integral system. Actually, exact results can give the, if it takes the the size become very large, you can know that actually this system have this thermodynamic phase transition. Without this exact results, we cannot believe that everybody, I think, cannot believe that is true for the static mechanics and also quantum mechanics and Newton series. So exact solution actually gave the stand. I try to use the Chinese to 给一个基准，所有的东西都是给一个基准。那么现在很多东西呢，实际上只有你有严格的解，才能可能给出这样的基准。那么如果没有前面这些的解的话，大家不会相信这些理论是正确的。好 ，actually they have not of other examples. Actually, for the quantum integral system has many application in the strain gauge series. I think some people talk about ADS, safety correspondence, that actually quantum integral system have many application in this one. And also supersymmetry Yang-Mills, because the non-abelian Yang-Mills series actually is interaction systems. For the quantum case, if the supersymmetry is very high, then this system, we call it integral system, because some sector you can use the quantum integral system to get the result of that. And also the static mechanics. And the quantum integral system, the first one actually is start from the IC model. I think also this is become a small area of the physics and also mathematics, because the static mechanics, and also they have another models can solve. And also they have the application for the constant metaphysics, actually mostly in the 1+1 space and times. So very famous one, the supersymmetry TJ model, relate to high temperature superconductivity. And also the Hubbard model. I think it is most popular constant matter physics is Hubbard models. And also because the system, if the quantum integral system conserve charge relate the symmetry of the system. So actually, for the quantum integral system, they have many very large symmetry. That means they have some relation with the group series and the extent of the group series. So they have the actually the study of the quantum integral system at has given very important influence to development of the quantum group and represents 表示理论 and also have some application for the algebraic topology, and also in I think 10 years or 15 years ago, the very popular one is non-commutative geometry. Actually, is related the quantum integral system. So this system is integral system. That means is of course this system is the a strong copying system, and this system, because they have a lot of symmetry and can exact solve. Actually, here, because it can exact solve, that means you should have developed many methods to solve this system. In history, actually, the first one to solve this is the Hansen Bate. Bate, actually, he's a Nobel winner. So that solved the system. I will give it as this example to give all the method how to solve the system. So so after his work, people call all the method to solve this quantum integral system to beta ansatz. And very important development in this small area is that the 17th, let's give the Australia mathematicians, Roger Baxter. He found actually all the quantum integral system spectrum, the conserved charge spectrum have some universal structure. This actually relate to the symmetry of these systems. And a very important development is from the Faddeev group. Actually, they invent a very popular, very powerful method to solve all the based on the Yang-Bass equation integral system. This method actually is the most powerful method. And also after that is happened in the end of the 1917s. And after his work, almost the Yang-Bass solved the integral system can solve to use this method. And also found that they have the exceptional one. This exceptional one actually cannot solved by all the method. This is three methods. And all these three methods actually based on a very technical one. They're based on very, the special structure. Should have some reference state. That means they should have some U1 symmetry. This is related in constant matter physics. That means the quasi-particle number should fixed. That's the so this system you can decompose the whole Hilbert space by the number of the quasi-particles. Because they have the U1 symmetry, this number is fixed. And after that, people found out they have the group, and the most important group cannot solved by this three method. In this, people interested in this small area try many ways to how to solve this one. And we are lucky in the 1913s, we together with the Professor Yupeng Wang in the Institute of Physics, Chinese Academy of Science, we together to solve that. Actually, we have tried many methods and tried to find a way to solve that for many years. I was the postgrad student start from the 1990, so that means more than 20 years. I only focus on this particular area to try to find a way to solve it, because the Faddeev group already developed a very powerful method to solve most of the system. But at that time, we know that exception one, we try to get that. So we are lucky to find a way. This way, about to now, seems to very universal method to solve all the system of the quantum integral system. So I will use the particular example to find out why these three methods cannot solve this one, and why our method can solve that. So that is big. So the first time, so in this in the first lecture, actually I gave the review about this Fatih group to the method. This method actually before 1913 actually is universal way to solve the system, but only for the particular systems can use this method. And this method actually is related to the first one because U1 symmetry. And also, they use this way, you can prove that Yang-Bass since the quantum integral system, the spectrum had the uniform structure. That's actually is Bakes TQ structure. So the first lecture I gave the review of this method, and in this afternoon I will give about our method and our method how to solve all the system, and also the system cannot solve by all of these methods. So that means the first is the U1 symmetry system is with periodic, actually is periodic boundary condition. And and another one is the diagonal term. So let's start from our particular example. That is the Heisenberg spin chain. This spin chain actually is the Heisenberg first introduced this system, this model. In physics, that means we start one dimension space. So let's we have the lattice of the size of the n, and each side we have the spin 1/2 systems. Spin, we call it spin. Actually, they only have the nearest neighbor interaction, and all the interaction coping constants of the three direction is the same. This is the first one introduced by the Heisenberg to try to explain the magnetics in Soliton systems. And this system, from the bulk interaction, you know that they have the rotation around the spin, around the direction, three direction, because the coping is same. That means you can any choice x, y, z. If the rotation, that the interaction except the boundary. In both cases, they have no change of the interaction. And if you impose the periodic boundary condition, that means you joint the beginning and the end together. This system also, this particular boundary condition means that this system also have rotation around three directions. So that means the total angular momentum is constant charge. If you choose z direction, that one, the total spin in the z direction is good number, quantum number. That means this is fixed, cannot change. So if the Hilbert space, you can decompose in terms of this total spin. In each subspace, you can diagonalize this Hamiltonian. Actually, this Hamiltonian have even more conserved charge and a very powerful method. So here, besides the total angular momentum, and they have a lot of conserved charge. Sorry. So here I didn't give the give the expression of the all the conserved charge. Actually, because this quantum integral system, you can have the standard way to construct all the conserved charge in the following way. So the conserved charge, commute conserved charge, that actually is the abelian conserved charge. You can use another generation function in this small area we call it transfer matrix. That's the generation function. You can give the function and as the function of the u and the coefficient actually is all the conserved charge, all the operate in our Hilbert space. So if you know that, you expand of the with the u, you get all the coefficient. And if you use a conserved charge, you can use this define the generation function. This nothing. This equal each other. And for this particular Hessian spin chain with periodic boundary condition, you can in particular way to construct this one. Actually, we can introduce you don't need to consider the detail. I only explain that you can stand a way to construct all the particular conserved charge. In this way, the technique is to introduce some particular matrix, this 2 times 2 matrix, and this matrix actually each element is operate. It depends on the spectrum. Depend on this particular parameter u. In this small area, we call it spectral parameters. And how to construct that way? We start from a particular R matrix. This R matrix first found by the Professor Sein Yang. Actually, he gave the very important contribution for this small area. I try to use Chinese to speak very 更准确一些。杨先生在他的在清华的纪念他的在物理各个领域的贡献的时候，他应该做了一个水晶的一个12面体，里面呢，当然他有非常多的贡献。至少在 mathematics physics 这个上面，他把杨马斯方程是作为他自己的一个贡献刻在上面的。那么这个 R 矩阵呢，最早就是杨先生给出来的。那么 ，so you don't need to go the detail about how to construct in this particular one. So start from the particular Yang-Bass equation R matrix. You can construct this particular matrix, and A, B, C, D actually is the operator, depends on the spectral U and on our real Hilbert space. And build up, so you just know that it's enough. That this R matrix is not arbitrary R matrix, two-body R matrix is particular one. That so how to construct this one? So very important one is that. So we know that our Hilbert space is the lattice, and the size number is n, large n. Actually, this n is a very small one. So for this R matrix is depend 2 parameters. Actually, I should mention that. Actually, the 0 space is the 2 dimension 2 space Hilbert space. Actually, this from the 0 space you can decompose this 2-body one as the 2 times 2 matrix, and each J corresponds to another 2 times 2 on particular Hilbert space. Let's start from the 4 times 4 matrix. That is first one gave the same Yang net. So you can decompose this 4 times 4 matrix as the 2 times 2. Each one is 2 times 2 matrix. And this actually is action on the Hilbert space of the 2 dimension. That is correspond to AJ, BJ, CJ, DJ, action on this particular Hilbert space. And then, because the structure of the monogeometry matrix, the whole space is actually 2n times 2n Hilbert space. And each subspace, each side, we have the 2 dimension 2. That's you can use this particular way to construct the capital A, B, C, D start from. So, so for the particular one, if you take the n equal 1, the whole the size equal 1, we already know that the capital A just this one, and capital B actually this one, C, D is this one. So for n equal 1, actually we have the A, B, C, D, this one. How to get the n equal 2? So you can use this structure, you can get n equal 2 case. That means capital U actually you can express in terms of the some operator only on the particular subspace of the J. Actually, this way is in the mathematics, this actually is coproduct. That means you have the structure on one side, the operator on one side Hilbert space. You can use this way to construct another one on the whole Hilbert space, inside Hilbert space. But most important one is that no matter how many n and how many, we have the spectral particular choice or the number theta depends on each side. So no matter how large of the n, how choice of the theta j, actually because the fundamental one, this 4 times 4 matrix satisfy the particular equation. Now people call it Yang-Bass equation. And because the build-out block, so let's return to the here. Start point this the R matrix, because this R matrix decomposes of the 2-body matrix. Then this particular choice of this R matrix. This R matrix actually satisfies the Yang-Bass equation, is solution of Yang-Bass equation. If you use this R matrix, use this one to construct operate capital A, B, C, D. I use the coproduct structure to how to construct this A, B, C, D in terms of some polymetrics, because in each side you have the 2 dimension. The operator only 4 polymetrics. So 3 polymetrics plus identity operator is all the 2 times 2 basis of the matrix. So that means start from the particular R matrix, you can construct this A, B, C, D. And because this fundamental block of this R matrix satisfies the particular equation, that is the Yang-Bass equation. So that means you construct this actually operate capital A, B, C, D action on the whole Hilbert space. That means each of this operator is the 2 power n times 2 power n, very large matrix. And no matter n how large, no matter theta you choose, they all satisfy the particular relation of this one. If you impose the block is the solution of this particular Yang-Bass equation, that means start from the R matrix that's given by the Yang 先生。那么 so that's from this one, if you take the choice, of this one, that means the capital A plus capital D. If you start from this R matrix, use this way to construct this A, B, C, D, then the sum of the A plus D is commute to each other. If you start arbitrary this R matrix, you can't prove that. So that means start from this particular solution of this fundamental Yang-Bass equation. You can use this way construct the conserved charge. Not conserved charge, they commute to each other. This operator commute to each other. Then you expand with the parameter u, you can the coefficient all the commute to each other. And our Hamiltonian, Heisenberg Hamiltonian plus the periodic boundary condition. This particular Hamiltonian actually can construct in this particular way. That means there is a coefficient of this generation function. That means all of the TU commute with Hamiltonian because this is just some particular choice coefficient. So that means the Hamiltonian, this way construct the transfer matrix, they commute with the Hamiltonian is a conserved charge. And also each other, this coefficient commute each other. That means all the abelian conserved charge. The proof of this one, you can use the diagram to, you can easily find out a way to how solve that from the particular block. That's actually, we can use the R matrix, the 4 times 4 R matrix can become the two-body R matrix, interaction R matrix. That's we have the this become the let's start one body space-time V is the 2-dimension linear space. So that's R matrix is 4 times 4. You can decompose it as the scatter matrix of the two-body one. That means that you can, this have the 2 index, one correspond the V and another correspond the V. So is the 4, because each of the factor space is the 2-dimension. So the tensor product space is the 4th dimension. That means the R matrix can decompose that Y. And this decomposed way actually, just like the here. So the first is corresponding to 1 2-dimension space. J is another 2-dimension space. So from the A, you can decompose as the 2 times 2. And each of the elements actually is the operator action, the J. And the J is 2-dimension space. So that means this actually, each block is 2 times 2. So in this way, you can use this diagram to stand for this R matrix is 2-body scatter matrix. You can think about that as that one. The Yang-Bass equation actually is that. So that means you can, here the 3 R matrix, they satisfy some product. And the Yang-Ballas equation means you can move this 3 line in this way. So this means this is the standard to the Yang-Ballas equation. So this actually is the Yang-Ballas equation. You can use this way to stand of the Yang-Ballas. The rule is just a move to this line to in this one cross the R matrix. Then you found out actually only for one the space. If you have the n space, this corresponds to our T, that is capital A, capital B, capital C, capital D. Actually, the action on our real Hilbert space. So RTT equal TTR, actually you can use this way. The first line, you can move to here, then you can move another way here, then finally you can move all the operate in this way. So this corresponds to the proof of the So we start here and we finally get this relation. This relation can use the diagram from here, end of here. And this equation guaranteeing that the transfer matrix actually commute to each other. That means we can expand this transfer matrix as du, you can get all the conserved charge. And finally, because this T actually have this kind of relation. That means the operator capital A, B, C, D actually satisfies some relation. This relation, I give some of that one. That is A over A commute to each other, over B over C commute to each other with different choice of the spectral parameter. And A and B, D, they satisfy this kind of the exchange relation. From this relation, you can construct all the spectral eigenstate and eigenvalue of the transfer matrix. This way actually is a method developed by the Faddeev group in the end of the 17th. And because this system have the U1 symmetry, that's the total spin, Z direction actually is conserved charge. We can decompose the whole Hilbert space in some sub-Hilbert space. Actually, we can choose the particular state. That's all the spin. Each side is spin up. So we call this omega, all the spin up. You know that the SZ action on this all the spin up, that this is eigenstate of the total spin Z direction is the 2n/2. And this state, you can easily find the capital A as the operator action is the eigenstate with the particular eigenvalue, and the D also eigenstate. And this state is all the spin up, and the B the C operator actually is accretion operator. They made the flip the spin. Actually, because all the spin already up, so you cannot flip each spin any size of spin again. So that means C action on it 0. And the B, that's flipped down. That's sum of the one is flipped down. They actually create a new state. So finally they found a way that you can define the subspace. That means M spin. So the total number of spin of the M can flip down. This subspace can use this the B action M B action on this particular state. And you will find the SZ action, this all no matter we introduce the parameter lambda 1 to lambda m. Actually, particular different choice of the lambda, you can give different state, different states, but all the states in the same subspace with total number of the spin is the 2 n over 2 minus m, this subspace. The dimension of this subspace actually is the CNM. And you can find out, use the exchange relation of the A and B, D and B, you can find out that for general AU action, this one actually they have these two terms, D action on it also have these two terms. You can easily to get the action of the transfer matrix on this particular state into these two terms. Because the lambda, different choice, the lambda give different state. So if you choose the lambda in this particular way, this is called the beta ansatz equation. If you choose in this way, the third term actually vanish. That means the transfer matrix actually, this particular state is the eigenstate of the transfer matrix, because transfer matrix is concept charge generation function, abelian concept charge generation function. That means they can simultaneously to diagonalize. So that means if your choice this lambda j satisfies the equation, beta ansatz equation, that this state actually is the eigenstate of the transfer matrix. And the most important way results is that actually the eigenvalue can be right in this particular way. And this Q actually is the polynomial of degree of M. And so from the constructor, that's the eigenvalue of transfer matrix should be some polynomial of degree of M. And here, because this structure, you can see that the eigenvalue lambda u as the function of u is not polynomial, because they have some pole here is related to the roots of the polynomial of Q. And if the residues and this particular lambda j is 0, this gives the equation of that. That one actually is beta ansatz equation. That means beta ansatz equation actually guarantees that this function is the polynomial. So this way actually the first found by the Baxter. He found out that all the integral systems use the R matrix start from the Yang-Bass equation, especially for this here. This particular example is related to SU2 algebra. For SU2 algebra, you can solve that all the transfer matrix, the eigenvalue can be parameterized by some Q function in this universe relation called TQ relation. And this function this polynomial lambda j, the rows should satisfy some particular equation. Actually, so the polynomial, we know that polynomial is parameterized in this way. First, for me, I think it's very strange because the polynomial, we just choose the coefficient or itself, the rows, then we can determine the polynomial. But here, use the particular weight. And also this way plays some universal role in integral system, the concept of charge. And actually, this way, here I gave the example to use the particular construct, the eigenstate. And use this way, you can easily find out that actually the eigenvalue can be used this way. So actually, for this particular system, first solved by the Hansen beta, actually, if in that time, why Hansen beta to get this result actually is based on the first I told you the integral system, the picture. That means if the system is integral, then that means you can use some kinetic transformation for the dynamic systems. That's the kinetic transformation to the factorized becomes some kind of the free particles. Free particles, we know that is some kind of use the I try to give some picture in Chinese. That means beta 解这个的观念是什么呢？这个系统如果是可击的，它有很多的守恒量保证了它一定在某一个 picture 里面，它是 factorize 以后，它就是自由的，它可以用平面波来展开。那么这个只有是可击系统才有的。那么平面波的展开，它得到了它的解，它的所有的守恒量，如果你写出来的话，它必然是这样的一个结构。这个结构呢，就是实际上在刚开始，它只是看不同的模型做出来结果都是这样。这个一定隐含了很多的结构在里头，很多的。而可击系统是一个非常特别的。我用中文来讲吧，因为大家都是都能听懂英语的话，我讲的不一定非常的准确。把这思想，我想把思想给大家讲出来是更重要的。技术性的东西，也许你可以跳过。如果你感兴趣，你再仔细的去把它去关注一下它。那么这个最重要的，我想最重要的是一种思想。那么 Baxter 呢发现了它这样的一个结构以后，他告诉所有的可击系统，就 SU 二代数有关的，它应该都是这样的一个结构。后来呢，很多人都是想的应该是这样。法列夫学派给出来的代数贝纳赫兹方法以后，你去解出来，它一定是这样的一个结构。那么它的结构呢，就是刚才我虽然是做了一个例子，那么它严格的依赖于这个问题，就是它把它所有的本征态，在一个子空间上，因为它有 U1 的这个对称性的话，它在这个子空间上呢，它可以用一个参数，用 m 个参数把它描述出来。那么这个 lambda 取任意值的时候，把这个自旋是n 减 m 的这个子空间全部的都张满了，这些态都把它张满了。那么也就是说，我用一组参数把它的本征态在这个子空间的本征态能描述出来。而且呢，我这个transfer矩阵作用上呢，它是一个很特别的一个结果。那么我很容易就选择这个 这个参数满足一个方程的时候，就是它本正态。这个是足够聪明的，就是我们一个 m 乘 m 的一个矩阵，我们找它的本正值，找它的本正态和本正值，这两个是相关的一个问题。那么这种方法做的关键是什么？我猜到它的本正式是长得什么样子，我可以用一组参数把它描述出来，然后我把这个矩阵作用上去，我去看这个参数满足什么条件下，就是它的本正态，那么你也就给出来本正值了。这个是足够聪明的，对吧？如果这个 m 大，我们这里面碰到的是2的 n 次方乘2的 n 次方的这样的一个矩阵，你几乎随这个 n 增大的时候，你几乎不可能，你没有那么聪明来做到它，而你只可能用它的对称性来做。那么这个情况做的时候，因为它有这个总自旋的，角动量是守恒的，角动量是守恒的，我可以用角动量 z 方向，我可以把它分成一些子空间，在一些小的子空间我要来做，但是这个 m 确定的话，这个小的子空间呢，就是牛顿二项式的那系数 Cnm。那么这个 n 和 m 都非常大，对应的这个数也是一个非常大的一个数。那怎么猜到这个？对 U1 对称的系统呢，它可以用这样。那么贝塔最早做这个的时候，它基于一个，也就是说，它一定需要这样的一个总自旋朝上的这个态作为一个基础，这个把它叫做 reference state。那么我去翻转它，那么一个 b 作用上去就有一个位置翻转，然后前面再加一些这些所有可能的线性组合。那个 m 的那个呢，也就是有 m 个翻转，那它的 choice 就是 Cnm， 然后把这所有的系数进行一个特殊的组合，就能给出来。那么这个东西当 m 和 n 非常大的时候，你是没有办法猜的。那么唯一就是因为它这个出发的这个 R 矩阵呢是满足杨巴斯方程，然后我构造出来这个大的 T A、B、C、D， 它满足一个朴实的二次关系。那么正是由于这两个性质呢，就可以使得你把这个构造出来。构造出来以后呢，那么从这儿已经马上就完了，时间也差不多了，马上就完了。这里面我只告诉一个大家，那么从这个结构上来看的话，从构造的话 ，lambda u 是一个 n 阶多项式 ，n 阶多项式我只需要它 n+1个系数就知道了，对吧？而这个多项式呢，它 leading term 最高阶的是2，从它的构造就可以看出来。那么实际上需要 n 个条件把这个多项式就能定出。而这种方法呢，它是根据技术性的一种办法，虽然这个设计的空间都是为数非常大的，但是它有一个规律性的构造出来，我这个大 A 大 B 大 D 大 C， 我的态呢也可以通过特殊的情况。那么这种技术方面找出来以后，发现呢，它可以用这样的一个朴实的形式表示出来。那么这种表示形式呢，当然后来大家都叫的 Baxter PQ， 实际上这在高能理论里面有特别是跟可积相关的一些里面，它都会出现这样。那么这样的结构呢，当然，如果你是第一次碰到这个的时候，你肯定觉得这个很奇怪。对于我个人，我自己第一次看到它，我也觉得很奇怪，为什么我要用这样把2的 n 次方的，因为你 Hilbert 空间是2的 n 次方，所以用2的 n 次方的这样的 lambda u 呢，用这样一个看上去非常奇怪的一个形式把它参数化。那么它参数化的这个参数呢，就是 lambda j， 它必须是这个方程的一组解。那么给出这个方程 m 个的是 n 个未知数 n 组方程，你给出一组解以后带进去，就给出一个 lambda u， 所以把 lambda u 用它来参数化。那么能量的话，刚才我们是劳格导数，那这组解你找出来，那么对应的能量呢也就会找出来。那么这种方法呢，我们所有做的问题不是一个非常一个 particular 的一个 n 或者一个m， 而是任意的 n 任意的 m 都能把它解。那么 这是刚才周期的，我下面一个更快一点的来讲另外一个模型。我把这个链呢拉开，原来我是把手跟尾粘起来，这是一个周期的边界条件。现在呢，我把它不粘，就是拉开的。那么体内的相互作用还是这样的形式。那么我给两个边上加两个磁场，那么磁场呢，这两个磁场是平行的磁场。那么这个就是最一般的这样的一个模型。那么为什么是这样呢？因为体内它是可以三维空间可以转的，那么也任意的转动它 SU2 的转动它都是不变的。那么也就是说，我可以把这两个平行场呢，这个我选的转成 Z 轴，沿着 Z 轴。那么另外一个跟它平行的一定也是 Z 轴。那么这个是最一般的两个平行场的情况下，主要是因为它体内的是三个方向的相互作用的系数是一样的。那么这个是最一般的，这个系统也是可及的。那么这个证明它的可及，就是我要找到一个abelian 的 conserved charge 的它这样的一个生成函数。那么这个呢是在88年 ，Scanning 是法列夫的一个学生，现在是英国皇家院士。那么他找到了一种方法，这个方法呢实际上就是他们方法的一个推广，把它解出来了，发现它的谱呢和刚才是一样的，只不过是 A 跟 D 改变了，这是因为开边界的原因。还有一个呢，对于这样的一个系统呢，你去看它的对称性的话，你很容易。虽然这两个磁场加上了平行的，原来体内是三个方向任意的旋转都对称的，现在呢，它是平行的，我把它放在 Z 轴，那也就是说，它 SU2 的对称性现在 broken 到绕着 Z 轴旋转的时候，这个含分量是不变的。刚才的总自旋 Z 方向的这个分量呢，还是守恒量。那么用这个守恒量呢，我也可以把黑本的空间跟周期一样，把它用那个 m 来参数化。那个 m 整数的话，代表是总自旋是2分之n减 m 的这个子空间，我也可以把这个所有的本征解出来，给出来。它可以也写成这样，这个呢，实际上是跟它的优异对称性是有关的。然后呢，这时候也是用这样的一个多项式来把它参数化的。这时候的 lambda 呢，不能是任意，必须满足一定的方程，就是后面的 BA 方程。那么，有点超时了，我把这个上午的这个解的这个结果呢，总结一下。细节你不需要知道，因为这个需要一些技术性的一些东西。但是结论呢，就是只要这个系统具有优一的对称性，它告诉你呢有一个 m， 这个 m 代表的是总自旋的 z 方向，同时呢它的原激发呢实际上就是 Mangalore 的激发，它代表的是翻转。如果用刚才那个 picture 来看它的话 ，reference state 代表所有的都自旋是朝上的。那么这个 m 呢，就是告诉你了，我把 m 个翻下来，它进行一定的组合，它就能把这个整个的这个子空间都能张成。在这个子空间上，它的守恒量的生成函数的谱呢，这特殊的守恒量的这个生成函数的谱呢，它都可以用这样一个参数化把它描述出来。描述出来呢，这时候呢，它的 lambda 这个 q 的这个根呢，它必须满足一个特殊的方程。这个方程从这个结构上来看的话，如果没有这个方程，这个是有歧义的。但是这个方程呢，保证了这个是一个多项式，那么不会出现歧义。那么我们构造的时候，这个 transformation 本身就是多项式。那么这个方法得到的这个解呢，是跟它的可及性是有关的，而且出发就是它的所有的守恒量的生成函数来给出来，所以只有可及系统才可能有这样的情况。而可及系统呢，它的谱呢， 又可以用这样一个朴实的关系把它描述出来。至少对于游玩对称的，刚才那个系统我们可以看到它的角动量的 z 方向的总自旋它是守恒的。这个守恒呢，就刚才我讲的那个 m 呢是代表翻转的个数，翻转了多少个。那么这个呢，它对应的，如果你让这个 n 趋向无穷 ，m 也趋向无穷，你去看它的基态的时候，它的基态呢，在反铁磁的时候的基态的 m 呢就是 r 分之 n。那么呢，总自旋是等于0的，它的激发呢就是有一个翻转的。那么这个刚好就对应的翻转的产生的一个翻转，我们把这个产生的这个准激发的这个呢叫做 Magellan。那么 m 的不同代表呢 Magellan 的个数的不同，所以这个系统呢一定是总自就是离子数守恒的这样的系统。那么我稍微把下午要讲的这个系统呢，刚才周期的我们知道它是具有三维空间的旋转性，对这样平行场的时候呢，它就具有绕 z 轴的这个对称性。那么这个都保证了我们会出现后面的 Magellan 的激发。那么 Sciani 呢，在88年他证明了，对于这两个边界场，你可以取任意的，不一定平行，任意的两个边界场的话，对于这个系统都是可及的。可以找到它的守恒量的阿贝林的守恒量的生成函数。那么88年的时候，他给出来这个解说，他当时就意识到，如果这两个场不平行的话，是没有办法用他们发展出来的这些方法都要解的。所以从88年之后，这个小领域的人都希望寻求一个办法，能把这样的可及系统也能解出来。那么这个如果不平行，大家很显然，你绕着 z 轴的这个旋转对称性也是没有了。那么这个系统怎么样呢？来解的？那从88年之后一直到13年之前，没有人给出了一个正确的解。有人号称给了解，但最后大家都发现他的是错的，他只可能在某些特殊情况下，这个 n 和 m 是特殊值的时候才是对的，其他情况都是错的。那么这个问题呢，也就是我是从90年开始做科研的，那么从那时候我一直在做这个领域，实际上早期在90年，在80年代到90年代中期，实际上是非常热门的，不光是在咱们国家，在整个理论物理、形式理论这都是非常热的。那么刚好我是90年第一个就碰到这个问题，然后一直反正这些年一直在坚持在这方面做。那非常幸运的是跟王云鹏老师，刚才我讲了王云鹏老师是做过中科院物理所的所长，他做了2届的所长，他在17年的时候是退下来的。那么他非常年轻，他是很早就拿到咱们国内的结青，应该是就前几届的结青，他在38岁的时候就拿到了结青是上限年龄45岁，在他那个年代，他应该是如果有现在的政策的话，他一定还可以延续下去，因为他真正是做零基态物理的，他的物理图像非常清楚，我非常明晰。而且他不光是一个战略性科学家，也是一个战术性，各个方面也都非常强。我非常幸运，后来在国外走了一圈，在这个小领域的很多人都很多非常有名的专家，特别主要是前苏联出来的，都进行过讨论，一直在探索方法，但是都没有找到。后来幸运的回来跟王老师那阵他还是物理所的所长的后期了，他也打算回归到科研，我们很幸运的在一起。那么实际上在这些年在国外，他在国内虽然有很多的行政的任务，但实际上他一直也在探索这个问题怎么样解。那么刚好我们很幸运，我09年回到国内的，那么 我们开始一起合作。那么最终我们把这个问题解了。那么解呢，实际上有些在这里面我讲它的没有讲细节，但它解的结构里面有些引申出来的，它就是一个多项式。后面我们找到的方法就是用多项式的分析可以把这个问题求解。那好，那时间没有控制好，那么非常抱歉耽搁了大家的。我希望呢这样的一个东西呢，把思路给大家，因为这是一个非常 technical 的一个东西，希望思路能给大家。好，谢谢大家。
好，非常感谢杨老师给我们对这个 algebraic Bell ansatz 这个方法一个非常清楚的介绍。大家还有没有什么问题要问杨老师？
老师，非常感谢您的讲解。就是我更关心这个可及系统在超对称理论里边的应用。就是我之前看到就是这个和塞伯格韦特理论有联系，但是我不太清楚这个具体的联系是怎么样的，以及就是在比如超对称里边的可及系统的话，这会不会出现像Yang-Baxter方程类似的东西？
是的，它有可能还突破这个。那么刚才我讲的一个例子就是比较高的超对，特别是 n 等于4的4维空间的样面式理论 SUN 的这样的一个样，它有两个方面，一个 SUN 的这个 n 非常大的时候，它会出现可及只落在平面的这些图的话，它的可及。那么它对应的里面呢，因为纯的仰面色理论实际上它是一个没有质量的，它是可以量子意义下是都可以可及的，对吧？它里面的反常维数很重要，它的反常维数最终可以刻画成这些杨巴斯可及的自旋链的一个它的谱的问题。这个是跟它是有，我对这方面设计的并不深，但我知道这个肯定是一个重要的练习。
塞伯格韦特是 n 等于2的
啊，
对 n 等于4，但是有一本塞伯格韦特的可及性其实已经研究得很透彻，有一本书叫 塞伯格韦特 Theorem and Integral System， 你可以找那本书来看。
可以找那本书来，这个是比较成熟的。我这个设计的自旋链的这部分是后来弦理论里面也出现，n 等于4的仰面色理论里面也会出现的。
好的，谢谢老师。
大家还有其他问题要问杨老师吗？好，如果没有的话，杨老师下午还会给我们第2堂课。我们再次感谢杨老师。
好，谢谢大家。
谢谢杨老师。
没有，我把时间没
事。因为讲 algebraic Bell ansatz，我其实因为我在 Stony Brook 上。